Good morning, everybody. I'm just checking to see if you can hear me, and then you can see the my introduction slide. Okay, thank you. Okay. Well, good morning, everybody. This is our third lecture, and we're going to talk about a very important aspect of fluidized beds, and that is the process of gasification in fluidized beds. As I touched on it several times, as we have become very conscious of higher efficiencies in any kind of thermal conversion, including power generation through thermal processing. We are aware of two things. One is, of course, it's consequences of burning solid fuels or fossil fuels, and how can we minimize this? At the same time, how can we meet energy demands in a way that will have the minimal effect on the environment? So gasification is one of those important considerations that many operators have taken into effect from power generation to various chemical processes. So to be able to really understand the fluidized bed gasification operation, we have to have a good understanding of what gasification is, what it involves, what parameters, and how it's done. So I'm going to start with a little bit of background information, and leading to all of these, when we put all of these tiles together, it will lead us to a very obvious solution, and that is a fluidized bed gasification process. So to get there, I'm going to introduce three things very quickly. The first one, of course, is the combustion process, which is an essential and integral part of gasification. As we all know, we touched on it several times. It's quite basic that combustion is a chemical reaction, basically, and it takes place, it happens between fuel and an oxidant. Typically, of course, it's oxygen in the air. And the outcome of this reaction is in the form of heat and light. And we are, of course, when something burns, we see it in the form of flame, but it also produces heat. That is our primary concern here. Pyrolysis, I'm sure you're aware of what it is, but it is, again, it's important to understand fundamentals of what it is, why it happens, and how it becomes an integral part of, again, a gasification process. It's basically a thermal decomposition. It's a process, chemical process, that occurs in the absence of oxygen in an inert environment. When that happens at a given range of temperature and in the absence of oxygen or very little oxygen, it breaks it down into organic material, the organic materials in the fuel into solid, liquid, and gaseous products. Okay, so understand one thing: combustion, I will elaborate more, happens in the presence of oxygen. Pyrolysis happens in the absence of oxygen, and they go hand in hand in a gasification process. What is reforming? Reforming also will happen. We will introduce in our gasification process. It's a process that converts hydrocarbons, or let's say alcohols like methane, methanol, into a syngas. And what is syngas? It's a mixture of hydrogen and carbon monoxide. And in the reforming process, of course, steam is most commonly used, that we have, of course, oxygen and carbon monoxide present. Okay, so what are the types of reformers? And of course, steam reforming is most common, but you can also have dry reforming, partial oxidation, and several others. Then, what is gasification then? It is a chemical process again that converts carbonaceous material, that is a biomass or fossil fuels, and mostly, of course, again, in our case, will be coal, into gases through high temperature reactions, typically over 650, 700 Celsius, and the product that is yield is syngas. Again, as I mentioned, what it was. So this is a process that is not combustion, but it is aided by or through combustion in this process, because you will, if you go back to your basic kinetics, you will know that gasification requires heat input into the process. So therefore, it is dependent on some sort of heat supply in the form of combustion somewhere in the process. Why do we need it? Again, I emphasize the need for clean energy production, and of course, many chemical syntheses, such as methanol or ammonia production, that are absolutely essential, of course, for a variety of reasons. For example, you cannot make fertilizers if you can't produce ammonia. What are the advantages? Reduces reliance on traditional combustion processes, so you don't need to burn them. Versatile use of feedstock materials. Let me share an experience with you. Many years ago, I had a delegation coming to my lab from Sierra Leone. Sierra Leone is a small West African country. Their main livelihood is rice. And they asked me if I could design them a portable combustor to get rid of mountains of rice husk that accumulated where their rice mills were. Having patented and commercialized a number of serial straw gasifiers using bubbling beds, I said, well, why do we need to burn this? You're burning your money, basically. If you incinerate this, you can gasify this, use the gas in diesel engines that turn your rice mills. And because of that, they saved millions and millions of dollars. Otherwise, they would have used to buy oil. So just an example, again, the versatility and ability to convert this into a really valuable commodity. So let's take a little deeper into the gasification. If you go back the history, and it started in 1812, actually, in London, the London Gas, Light and Coal Company. They commercially produced gas from which they called it town gas from coal for illumination, so they could light up their street lights. So from there, it's gained a lot of momentum and became again a big part of utility industry. The best way to define it, it's done by Van Zweig. It's the aim of gasification process is to transfer the combustion value of the solid fuel, okay, to gaseous energy carrier. Okay, I go over it slowly. You have solid fuel. When you burn it, you get a certain amount of conversion of its chemical energy into a thermal energy. In this case, you have this value without burning it and convert it into a gaseous energy carrier. You can burn the gas, but you can also do other things with that. And then this is preferably in the form of chemical energy, not in the form of sensible heat. Okay, this is one of the best definitions of gasification that you could use. Uh, the resulting gaseous fuel, compared to original solid fuel, it is easy to clean compared to the solid fuel again. It doesn't mean that a cleaning of produced gas is an easy task. It is very, very complex. We'll touch on it later. But it can be burned again after you're able to clean it efficiently in gas turbines, furnaces, boilers, and even internal combustion engines, or even in fuel cells, provided that it is very, very clean. Okay, so for a given fuel, the volume of the gas obtained from the gasification is much less compared with the flue gas obtained from a combustion system. Okay, so there's a difference, much smaller volume, but carrying the same energy content of the original fuel. Therefore, your cleanup system is much smaller compared to a flue gas cleaning system. So this table will give you a good summary of distinctions between the three chemical processes: combustion, gasification, and pyrolysis in terms of oxidizing agent, typical temperature range, principal product, and what are the principal components of the gas produced. In combustion, oxidizing agent is absolutely, definitely greater than the stoichiometric amount of air or oxygen supply. We talked about this, if you recall. I used the excess air concept and how much of it we use in fluidized beds and how much it was in pulverized coal systems, whatever, or how much of it will be in a car engine. Okay, it's always to achieve more oxygen to per unit surface area. You always supply more air than is required for the stoichiometry. However, in gasification, the amount of air or oxygen is always less than the stoichiometric amount. In other words, in plant technology, we call it you starve the reaction to oxygen. Okay, you don't supply, you always leave the reaction hungry to oxygen or hungry for oxygen. Okay, so whatever the oxidizing agent is, it is less than the stoichiometric amount. And in pyrolysis, as I said before, no such thing. It has to happen completely in the absence of oxygen, or if you're using steam. Temperature ranges, if you see, for combustion and gasification, it is anywhere between 800 to 1200, but not usually over 1200. We don't want to go into the Zeldovich zone and produce NOx. And in pyrolysis, as you can see, this range is held. Therefore, the temperature range is much smaller. Okay, so remember, for pyrolysis, lower temperature, and no oxygen. So what happens then? Combustion, as I said, the product is heat and light. In gasification, you still have heat because the amount of oxygen you've provided, that oxygen will oxidize the reactant, the fuel. Therefore, there will be heat, but also there will be combustible gas because of pyrolysis is happening within there. And heat and combustible liquid, in this case, pyrolysis case, and combustible gas, they are the products. Excuse me. In combustion, the end result is you want to ensure that all your carbon is converted into carbon dioxide to maximize the heat output. And of course, you have water vapor. Yes, I just heard you. Yes. Oh, I am actually. I don't know. I am coughing a lot, so I try not to cough in your ears. But is it better now? Okay. All right. I'll lean forward. And pyrolysis, of course, is a lot of carbon monoxide and hydrogen again there. By the way, if you like, I keep going, but if anybody has any questions, please feel free to stop me, okay, and ask me to repeat or explain better if something is not well understood. Okay. And I wish we were doing this again in person, but anyway. So the application then, if you look at this chart, the gasification will result in what we call syngas, short for synthetic gas. And syngas will have three outputs. You can use it in combined heat and power. I'm going to spend just a very short minute on this one. And of course, high temperature heat if you need heat for various processes. And you can also use it as a co-firing agent, co-fired usually with natural gas. Okay, so I use the term combined heat and power. I don't know how familiar you are with the IGCC process, integrated gasification and combined gasification combined cycle. Most modern power plants utilizing fossil fuels use fossil fuel, could be natural gas or oil or coal, use IGCC because you combine power generation together with heat for, let's say, from district heating to pro-supply and process heating, and therefore your plant efficiency is much higher. You minimize the condenser losses this way, okay? And you get to use both a steam turbine and gas turbine at the same time. Therefore, you have much higher efficiency. This is well beyond the scope of what we're covering here, but please understand that the reason why we are doing all of these things, the end result is mostly in power generation industry is to be able to use it in an IGCC plant top. So what are the sequence of reactions and gasification or coal and biomass? By the way, I will interchangeably use or give examples I use in coal or biomass. Okay, they're both very important, and I will from time to time use coal, time to time use biomass as example of fuel. So feedstock is either one of them. The first step is pyrolysis. First step is always pyrolysis because it takes place, as I said, at a lower temperature, and it doesn't require oxygen. So you have a whole bunch of gases coming out of pyrolysis process, in addition to tar and oil and char. Okay, so tar and oil, they are liquid, char is solid, and the gases, of course, they're gaseous. So you have three phases here. And gas phase reactions will have volatile matter combustion, and then, of course, water gas shift, reforming and cracking happening for them. And for the gas solid reactions, you have gasification and combustion, yielding the products as you see below. I'm going to open these up a little bit more, okay? But if you look at the feedstock side, again, woody biomass or agricultural residue and waste. This is the rice husk example I gave you. And of course, very importantly, residential and industrial waste streams, okay? In many modern municipalities, this is gasification is or incineration, but gasification is preferred because then you get to use the gas coming out of this. By the way, again, of interest to you, when I'm talking about gasification, it's through thermal decomposition. You can also have other types of gasification that some municipalities use. Again, it is through a different process, but we're only talking about thermal decomposition here. What are the limiting factors then of feedstocks? Size and impurities. In any of these examples, they come in different sizes and shapes and different compositions. Okay, even wood. Okay, if it's coming from one part of the country, will have very different characteristics. It could be hardwood, softwood. They will burn differently. They will behave differently. And same thing with, of course, the most complex one is the waste material. It has everything from fabric to shoes to anything you can think of in it. And of course, the strong effect is the moisture content in these that will significantly affect how we design our gasifiers. Okay, so in addition to that, they will all yield different amounts of tar. I will tell you in a minute what I mean by tar. They will have different heating values and ash content and melting behavior. They are all very significant aspects of the feedstock. If they are over a certain range, it is not worth gasifying it. You will be spending a lot more energy and infrastructure than the benefits you will get out of this. To go further, I should also tell you an important thing that you will have into consideration, that is porosity. Every single piece of fuel, and especially if it's coal or biomass, will have a porous structure, as you can see here. Nothing is, as I showed you earlier, like my tennis ball is like solid like this. They have pores inside. The more porous, the better, because it provides much larger surface area to mass ratio. Usually, we want in good coal 500 square meters per gram of surface area, surface to mass ratio, to achieve really good high level combustion. The other thing you should know, as I said, I go back here, it said feedstock limiting. You have to understand what you're feeding into your gasifier. How would you do that? You have to have something called, this is not approximate analysis, this is the ultimate analysis of your fuel. In this case, let me give you an example from a coal. This is um, 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 typical subbituminous coal that will have, you have to know its carbon content, you have to know its hydrogen content, you have to know its oxygen, nitrogen, sulfur, and ash. Of course, this is on dry basis. To be able to produce on dry basis, you have to also have the moisture content, okay? Why is it important to have this? This is the only way you can calculate, you can figure out the lower heating value or heating value of the fuel and decide whether it's worth gasifying or even burning this, okay? So you have to have this information. Without this information, you're blinded. You cannot do anything else, either as an operator or a designer. Let me give, again, go back to biomass. And in the case of, for example, rice husk, that we performed this years ago, you can either do it through a biological process and anaerobic digestion. Of course, it is. It takes a lot more time and, different facilities, or through a thermochemical process that will yield all these three products through three different processes. This is a really good map of how you evaluate your, which route you will take. It will take all these, okay, because they go hand in hand. Feedstock, if pyrolysis, in the form of its next step conversion. The primary product out of pyrolysis, as I mentioned, it's chars and oils, and they will be recovered differently than gasification. Of course, it's gas, and if it's combustion, it's directly heat. And where do you use them? You can, for the chemical industry, you have to extract them or synthesize them or upgrade them. Or if it's for the energy sector, you can use it, as I said, in various areas. And secondary products are here. This is a really good chart for you to understand the process, conversion process. So for something to be gasified, it goes through 4 basic steps. Drying, you have to dry the moisture out of it within the reactor or outside of the reactor, which was a very good question, was asked yesterday. Then you have to do it will go through pyrolysis or devolatilization. Then all the volatile matter will be released, will escape in an inert atmosphere and with heat. So remember, inert atmosphere, what's inert atmosphere? Inert atmosphere is where no oxidation reactions take place, okay, in the absence of oxygen. So we can put nitrogen there, but we don't want to put nitrogen there because we don't want to dilute the gas, because you cannot burn nitrogen. So gasification, as I said, again, it is an endothermic reaction. It requires external heat. It requires an external heat source, okay? And then, of course, combustion, it will happen with the oxygen reaction, okay? We covered most of this, so let me go over it. I used the term tar several times, and you will say, why are we talking about this? It is quite natural when you thermally decompose fuel, whether coal or biomass, anything, it will yield this liquid substance called tar, which is the mixture of various chemical compounds, and it's condensation of these chemical compounds. And they condensate at lower temperature or room temperature on solid surfaces. So imagine in any environment, if you are not dealing with tar, it will choke up your entire system. So it is important to understand how tar is formed and how you will need to remove it. Okay, so it has a very complicated formation pathway, and one of the one is called polyaromatic hydrocarbons. Okay, and if you're not, for example, looking after it, they are they are well known as a carcinogenic agent, for example. So you have to make sure that you remove all aspects of tar from your process. So when pyrolysis then take place, which is a separate thermochemical conversion process, it is not, you have to understand this, that we are not talking about a separate pyrolyze. We are talking about the pyrolysis reaction within the whole gasification process. Okay, and when we get to fluidized bed gasification, I will be able to explain it a little bit clearer to you why it is taking place at the same time. And this will take place at the given temperature range. Okay, so I repeat, you have the fuel, you supply heat to it, you have the gases released. This is the volatilization, and large organic molecules are cracked to form smaller structures. This is known as the metaplast, and then gases and liquid components migrate to surface. Then during the trip to the surface, some of the when I say surface, it is from within the particle. As you see here, I wish you could hit a pointer. Maybe I'll, yeah, here, my gases are migrating to the surface, and then they burn there or they're collected. And these gases are utilized in whatever form we want them, and the remainder solid one is char. You should also know that how much heat do you need to supply? You can choose to do under slow heating, where heat and gasification agent are supplied at different points, or fast heating, heat and the gasification agent, this case, which is gas, oxygen, steam, whatever, they're provided at the same time. Both end up with syngas, but in this case, the gas is a lot cleaner with less tar, because you don't allow it in fast heating for it to form as much as it would have if you were to heat it slowly. And the combustion, and we've touched on this many times, so I will pass this. This is your basic reactions for combustion. Now, any designer of engineering designer of a system, especially if you're designing this any type of gasifier, you need to take account the huge amount of moisture that will be present, especially in biomass. And in coal, there will be some, but biomass a lot. So you have to provide the necessary heat in order to dry the fuel so that you can burn it. We will be talking about fluidized bed drying later on, so I'm not going to spend a lot of time, but nevertheless, it's an important process that you need to take into account. The fuel must be dry. So let me summarize the gas part again. If you provide these different kinds of fuels, coal, liquid residues, natural gas, biomass, waste, whatever it is, to a gasifier. In here, if it's required, and mostly in modern system, it's required, you have to have a separate carbon dioxide capture and even storage facility. But aside from that, these are your products: ammonia, methanol, carbon monoxide, hydrogen, alcohols, Fischer-Tropsch fuels, waxes, and others, SNG, town gas, reduction gas, and gas turbines. These are all used for these kind of processes that will end up with these kind of products. Okay, so you don't just use the gases, syngas, or other products for electric power. It's only one element here. There are many other uses in chemical industry. If I may just speculate a little tiny bit, there will be a time that we will really not dare to burn or even gasify fossil fuels to produce power. They will be extremely, extremely of a high value commodity for many other products. Okay, so thermochemical processing, chemical industry will be in dire need for that kind of feedstock. So just maybe 100 years from now, but the day will come that you will not dare. It will be incredibly, incredibly expensive to burn fuel or gasify fuel for power production. It will come from other sources. This will be a completely different subject, but again, as engineers and the coming, you should understand that there will be a very different game plan for energy production. So, as I said, the product gas will come in the form of these gases: CO2, CO, H2, methane gas, and water vapor. And we will have trace amounts of higher hydrocarbons, inert gases, char and ash, tars and oils. They'll all happen at the same time. Okay, so what do we have in the product gas? The energy in the product gas is to a large extent chemically bound energy. Chemically bound energy, that means it has a lot of oomph. You can do a lot of things with it. And this is about 80% of it. If the gas cleaning system, or however, for gas cleaning system, for example, to remove tar, you have to cool it, okay? Cool it so you can condense it and remove it from the system. Then you have to do the opposite. You gain some energy, you have to put some energy to cool it, therefore you lose it. You account for 20% of the contained energy to be lost just for the cleaning process. So let me just jump ahead. As I said, one of the advantages or attractiveness of doing this gasification, and especially, of course, if it's pressurized, you can burn the gases in a gas turbine, even for internal combustion engines, but gas turbine. So you have to have very high pressures, high temperature, and gas is entering after it's compressed and high velocity. If you have a little tiny impurity, ash particle or solid particle in that gas, impinging on your gas turbine blade, it will destroy the gas turbine. Okay, So you will not dare using a gas or fuel in a gas turbine that is not properly cleaned. If you're using it in diesel engines, which operates at lower temperatures, then if it's not tar free and you have to cool the engine, okay, then at certain surfaces, especially at valves, tar will build up and it will stop working the operation. So please understand that when we are talking about these things, the hot gas cleanup on its own is a huge, huge subject. The companies spend a lot of money on this one, a lot of money. And also, there is, I don't know at your institution, anybody's working on it, but it is a very, very hot and current research topic, again, hot gas cleanup. Okay. So we have to you have to make sure that this is properly cleaned and also no carbon monoxide, of course, after the combustion process is left. So far, I covered a number of very basic fundamental aspects of gasifications, and I'm repeating it over and over that many things go hand in hand in terms of drying, pyrolysis, devolatilization, combustion, and gasification, okay? And how different aspects of reaction will affect what comes out of this. So as engineers, okay, think of it for a moment as a black box, okay? You have a reactor, you put a bunch of garbage in it, all kinds of things, and you will have gas coming out as an energy carrier, whatever you want to do it, transport it, store it, burn it, whatever you want to do it. The important question for you here, for 1 kilogram of that feedstock I put in, how much gas will I produce? Okay, this is the heart of the thing. Of all these things I'm talking about, you figure out what goes in and what comes out. For this, you have to understand all these fundamentals quite well. Okay. Gasification reactions, I'm going to just fly through them because there are an immense number of gasification reactions. I mean, it will be pages and pages of reactions, gasifications, and some very detailed models. Use all of them for the section, for the purpose of this one. These are the very basic gasification reactions that I touched on this. Basically, pyrolysis or heterogeneous reactions. You have these, and then combustion. You have the volatiles and oxygen, and of course, reduction reactions. You have 3 stages of them. You basically design your size and residence time. That is, of course, that will dictate the size based on the slowest rate of reaction, and that is the solid phase. Okay, and then these are the shift and reforming reaction. I think you should also know that of all these enormous amount of research and operation, there is still a model, that gasification model that is widely used both for understanding and calculations, called Van Loon's, and this is developed in 1950. Excuse me for a second, please. Okay, and according to the Van Loon's model, at the surface of the solid carbon, only endothermic reactions occur. Okay, so it takes heat from outside. Around the particle, away from the surface, carbon monoxide and hydrogen formed by the endothermic reactions, they get oxidized. So it has to take energy in order to release those combustibles, CO and H2, so that they can burn and give you burn. So this is a simple Van Loos gasification model that is shown here. I am going to pass through these reactions. Again, they are quite basic and fundamental. Basically, it has you sum them up in three categories: hydrogenation reaction, methanation reaction, and water gas shift reaction. So that's it for all the reactions. Let's move slowly towards the technology of gasification. Okay, and we will slowly come to the fluidized bed gasification process, but we're doing it slowly for everybody to understand the basics. So there are two ways of building gasifiers. One is through direct gasification, and the other is through indirect gasification. In direct gasification, you have energy and mass transfer. Mass transfer is the whole, like, of course, transferring of mass of fuel into energy. So they are supplied within the same reactor. Same as the question of drying. Whereas here in indirect, it is externally, energy is externally supplied into the reactor, and oxidation and, of course, whole mass conversion will take place. Drying pyrolysis, in this case reduction, and shift and methanation will take place here, whereas here it's just a reaction. Okay, so this is your choice of design, and how you will determine this will be based on predominantly the type of fuel you're using or feedstock for this. An example of indirect gasifiers. These are existing gasifiers. In one case, this is using gas, and part of the gas produced will be recycled back into in a burner, and you provide air, and it will provide you with the energy that is required for the pyrolysis and gasification processes to take place. The other one uses, instead of gas, char particles together with inert particles. That is an external combustor here, and this combustor will provide you with char particles and inert particles, and flue gas, of course, hot gases, and ash there removed. It goes into a gasifier to provide you with the required energy. So we divide the syngas produced into three categories, and you design your gasifier according to this category, because you will know, depending on your feedstock, what kind of gas you will get. It will be either low calorific value gas, medium calorific value gas, or high calorific value gas, having these components at different proportions. If it's a low calorific value gas, which is between 3.5 to 7 megajoules for in this case, feedstock, air, and recycled tars, they're all fed into a gasifier because we want to get rid of this removal. Then you have combustor, cooling, and everything, and the end either in the combustor, it's a straightforward combustor. You don't really care too much about air purity of the gas, and it produces heat and steam. And if you cool it and remove tar, then you can feed it into an internal combustion engine for power generation. Medium calorific value, it has a much wider range of application because it carries higher heat. Then it's worth the expense of pipeline transportation, and you can use other things. But one of the products again is methane, which you could use it through a reforming process in fuel cells, of course, if you want to. And then this is the high calorific value gas. This is the most desirable one. And again, basically, I had either methane or methane and CO2 after the separation. So the only reason why I'm mentioning these, you will know before you start thinking about your gasifier, what calorific value the product gas will have, and accordingly you'll decide on its end use. Two important things: pressure and temperature. Okay, pressure is extremely important. Gasifying under pressure has a considerable advantage, and you have much higher yields. And of course, as I said, it could become a very important and integral part of an IGCC, integrated gasification combined cycle process. And typical pressures between 20 to 40 bars, but it can go much higher and other. Temperature. Temperature is important. We want high temperatures, but the limiting factor for temperature is the melting point of the ash of the feedstock. If ash starts melting, if it starts softening, it will be sticking on every surface, every place that it can lend itself, and therefore it will destroy your gasifier. So you need to, it's very simple, of course, to find the melting point or softening point of the ash, and that will be your limiting factor, okay? Unless you do it in stages that you're able to remove the ash and then continue the process. Gasifying agent, it's either oxygen or air or steam. Of course, if in various power plants, you have separators that will actually separate oxygen from the air and feed oxygen into the system. Therefore, you avoid carrying unnecessarily all kinds of nitrogen in the air, which will not react, which is useless. It will take away the heat overreaction from you. Okay, we're going to spend just a few minutes on the kinetics, but I think it's been an hour since I started. Let's take a 5-minute break, and then we'll continue after that, okay? So it's 11 o'clock my time. We will reconvene at 11:05, okay? I should mention that this is still a very rigorous research subject, kinetics of gasification. But what we know so far is amongst the reactions in a gasification process, the slowest one. You need to know the slowest one and then do your calculations accordingly, are the heterogeneous. That means gas and solid ones that will dictate the conversion of the carbon. Okay, and you see these three reactions here. The rates for the water, gas, and Boudard reactions are comparable and several orders of magnitude faster than the hydrogenation reaction. Okay. All right. So let's quickly do an example. If you were to do this for a given fuel, how would you do this? So the Boudard reaction, you have carbon and carbon dioxide yielding into 2 moles of CO, and also it's yielding 172 megajoules per kilomole, okay, of energy. The reaction rate of carbon conversion, and we are assuming a first order reaction. That's usually a simplest way to do this is dCdt, of course. This is the rate of carbon conversion with time, and you have Km, the mass-related reaction rate constant, and C, CO2, is the concentration of carbon dioxide. Okay. The rate constant is, as you will all know, you have to find it, and it's temperature dependent. And we usually use the Arrhenius equation and do it in this form. So you have to have the rate constant. Rate constant is calculated through Arrhenius reaction, but you have to assume a first order reaction, and the E is the activation energy in this equation. The exponent, as you see there, I went the wrong way, and we end up with this expression. Then we will be able to then calculate how much of carbon is converted with respect to time. That will give us the rate of reaction. Okay, so it's a simple calculation, but you have to know your constants, which will be dependent on temperature of your operation and, of course, fuel. Effective particle size, you have to prepare them. The larger the particles, okay, if you use this one or this one, they will require a different residence times, okay? The larger the particle, higher the residence time. Therefore, your throughput of fuel into there will be much, much smaller, okay? If they're smaller, then you have to keep them shorter in the reactor or gasifier, then you can put a lot more of these and therefore produce a lot more gas. All right, we are getting there slowly. What are the types of reactors that we use for gasification? The most primitive or early ones, the counterflow gasifiers. Then you have the gasifying agent and fuel are in opposite directions. Then you have the co-current flow gasifiers. And the topic of interest to us is the fluidized bed gasifiers that you either have bubbling, stationary, or circulating one. And of course, a very high level one is entrained flow gasifier, which is a different subject. So we will be focusing on the fluidized bed from here on. But if you want to compare them and understand the range within which fluidized beds operate, either bubbling or circulating fluidized beds, you will notice the differences in temperature of operation, which is lower than the other two, downdraft and updraft. And they have a very, very, of course, the advantages, very flexible fuel flexibility, good efficiency to very good efficiency, and a whole bunch of advantages. But they will you will ensure that in either one of them, ash does not melt because of your temperature range that you'll build it, and the fuel flexibility again is superior. We talked about how fluidized beds operate, how fluidization take place, so I'm not going to repeat them, but in a typical bubbling bed, you feed the biomass and things happen, and in CFB, the same thing. Of course, I oversimplified these figures. They're very simplified. Tell me, what do you think the conflicting things? You have to provide enough air to fluidize the bed, okay? And you'll do this through a calculation of minimum fluidization velocity. What if the minimum fluidization velocity it carries with it levels of oxygen or air that is higher than the stoichiometric amount that will end up burning the fuel as opposed to pyrolyzing or gasifying it. So this is the zone, therefore, in whether it's bubbling or circulating, you have different zones. In close to here, you provide just enough air to incipient fluidization and also ensuring that the amount of fuel feedstock you're putting in, providing you with that carbon-oxygen ratio that is below the oxygen-carbon ratio that is below stoichiometry. Okay, then I can provide more air here as secondary, even tertiary air, to better fluidize and achieve all the advantages of fluidized bed because I have produced my gas. Okay, or there are various ways of balancing that conflict. So this is bubbling, this is circulating, and there is the twin bed that your combustor is a fluidized bed, and your gasifier is also a fluidized bed. In the combustor, you basically burn the fuel, okay? No pyrolysis, no gasification, straight combustion. Products of combustion, hot gases. You collect flue gas, but hot inert particles, okay, ash, sand, whatever, you feed it into it, and that will provide you the gasifier with the external heat source, okay? And then in return, you have to take some of the ash back into the combustor, and to serve as an inert material. Of course, you'll drain that ash from the bottom. This is very schematic, but this is the basic idea. So, key points of fluidized bed gasifiers. Bubbling bed gasifiers are suitable for small-scale applications with lower costs. Okay, so if you, again, like in the case of rice husk example I gave you, it was a lot more economical to because of the amount of supply and and the environment, it necessitated using a number of small bubbling fluidized beds as opposed to one large CFB. Circulating fluidized bed gasifiers are ideal for large-scale applications with higher efficiencies, of course, because of higher throughput. Twin fluidized bed gasifiers are particularly effective for biomass gasification due to their ability to handle high volatile content and avoid nitrogen dilution, because basically your heat source is in the form of hot particles. So we know some basics of bubbling beds, gas velocity, and everything. So let's talk about the advantages: fuel flexibility, uniform temperature, higher efficiency, and very critical, lower capital and maintenance costs. Inside the fluidized bed, there are no moving parts, okay? Compared to many other devices, okay? The only moving part is the blower underneath, which provides the air, and of course the feeders, but they're all external to the bed. Inside the bed, there are no moving parts. In any engineering system, moving parts are the main cause of failure or periodic maintenance requirements. In this case, you may need to go in and repair some broken refractory or accumulation of slag here and there, but other than that, maintenance cost and time for maintenance is very, very low. So in CFBs, again, you have much higher velocities. Therefore, you can put a lot more fuel in there than a bubbling bed, and it's a continuous operation. Then again, you can with this kind of operation, you're not confined to just one type of fuel. You can feed various different kinds of fuel, not too different from each other, because it will significantly alter, but you can still put different types of fuel into a CFB gasifier. Again, as I said, if you have really very large operation, like huge municipalities like New York, Toronto, Delhi, Mumbai, whatever, that you have enormous amounts of waste, and these are very, very attractive CFBs for these kind of operations. Again, I talked about the twin bed, so we'll pass this one. So, as I said, and let me again reiterate what happens in the fluidized bed. The fluidizing agent is fed through here. Fuel is fed here. So immediately, as soon as this happens, you have drying and devolatilization process taking place. Okay, this is the biomass particle. You have volatiles. First, of course, water vapor leaving, and then the volatiles leaving, end up char particles here. So from here on, you have inert material, you have char particles, and you have some of the gases, they are percolating through here, but most of them, they're also trapped in bubbles. They move upwards. Here is the journey of it, okay? This is a bubble. You have char, you have bed material, you have this emulsion, and here's a char particle, and they're all moving upward. As they're moving upward, the amount of air is increasing, the temperature is increasing because of some of the combustion process here. And of course, char particles, as they ascend in the bed, they're oxidizing. And finally, they are thrown into the freeboard, and char combustion will continue taking place until they're entrained out of the bed, and all of these reactions are taking place. Okay, this is the beauty of a fluidized bed that will take you through the entire journey from drying to devolatilization, char combustion, and gasification, all happening here, and they're corrected. I oversimplified this, but this is basically the reason why fluidized beds are superior compared to the others, considering again some of their disadvantages, okay, and which I will touch on later. Is this part clear? This is the heart of the matter. This is the entire reason why hundreds of industries, okay, utilities, chemical producers, whatever, they prefer a fluidized bed gasifier over some others because of its fuel flexibility, versatility, and its enormous ability to accommodate a wide range of fuels with different characteristics. So we covered these, okay? The flaming pyrolysis zone, what happens, all of these reactions take place. You have the char reduction zone, and that conversion of tar, methane, and char, again, still in the absence of oxygen happening in that zone, and then gasification reactions, then char gasification, and finally volatile oxidation. They're all taking place, okay? And this is, again, another summary of all of these reactions that are coming out of it. So what are the kinetic limitations? As I said, the solid phase reactions, they're the slowest ones. Therefore, conversion processes in the char reduction zone are kinetically limited. And then I showed you how to find the reaction rate. And then this will be the limitation. It will be conversion rate. Conversion process will depend on the reaction rate rather than equilibrium. And equilibrium, of course, is when they continue react until they reach an equilibrium. No, they will not. You'll not wait until then. It will be kinetically limited. How do we model and predict this? Simple kinetic models. That's what we will use, okay? Especially all my bubbling bed gasifiers. It was easiest and safest to use simple kinetic models to predict the performance of bubbling bed gasifier, and that includes gas composition and carbon composition. We are still depending on lab scale experiments to have empirical data and use this empirical data for scaling reactors up. This is the most risky part. Geometry, the wall effects, and all of those are significant, but yet it's impossible, even with today's huge computational capabilities, to properly model and predict these. So we use the kinetic model and experiments and find a happy medium. And we are also very highly dependent on the data from the operators. That's why when you go to a utility or any facility, they will guard their data very, very strongly because it is very important for them to to keep the data so that they could be the ones who could design and operate better, higher efficiency systems. What are the models again? If you want to, what are the methods to model these? As I mentioned, we can use equilibrium models, and equilibrium models could be either stoichiometric equilibrium model or non-stoichiometric equilibrium model. I am not really sure whether in your courses you have covered these kind of modeling or reactor chemical reaction technologies. But for you, just to have an idea, if you cover them, you'll know what I'm talking about. If you haven't, when you do, you will have to become engineers, or I'm assuming you'll become chemical engineers. You will know what they are. And non-stoichiometric one is more complicated. It's based on Gibbs free energy minimization, but it doesn't require predefined reactions. So what are the advantages of this type of equilibrium model? Simple and computationally efficient, provides a guideline for process design and parameter effects, but limitations are the hydrodynamics of is insignificant. Doesn't matter. It doesn't take into account the hydrodynamics. Okay, that means the bubble size, or all of those things. They don't matter. Or reaction kinetics are also not, because it's an equilibrium model, and it's less accurate in non-equilibrium conditions. Of course, that's quite plausible, but again, in the absence of all these tools, this is the easiest way to do this. If you want to be able to do a little bit more sophisticated, you can do a rate-based kinetic model that will incorporate hydrodynamics and all the transport processes like momentum, heat, mass transfer, and also reaction kinetics. It's more involved. It's more sophisticated. Of course, difficult to most of the time achieve convergence. Accounts for detailed reaction mechanisms, and again, more comprehensive and realistic, provides insights into spatial and temporal variations within the gasifier, which is really, really important for us to put design the interiors of the gasifier. As I mentioned, of course, when you put all these together, reaction kinetics, all the transport processes, including hydrodynamics and everything, it is huge, humongous, and therefore computational intensity is very high. It requires high capacity computations, much longer time. If you're paying for that computation through a supercomputer, the longer it takes, the more money you'll have to pay for it, but also you'll have to feed a lot of experimental data, especially for reaction rates and mechanisms. So you have a choice. If you're working for a very large company that can afford or an environment the high expense of very detailed model, you can use a rate-based model. If you are, you said, okay, I don't really care if my I can live within 15 to 30% of error band in predicting my gas output, then go with the first model. Okay, so we talked about these. There are also non-stoichiometric, we talked about this too, and here are the basics of it. I'm going to pass this. these are okay. This is what I wanted to talk about last. Syngas composition. So you look at different gasifier types. Downdraft fixed bed, updraft fixed bed. Pay attention to the particulate content in each case. See how small it is. And in bubbling fluidized beds and also circulating fluidized beds, it is significantly higher. Okay. Why? Because of the structure of the bed, and you have inert material, ash, all of those, okay, present and within the operating range. These are quite normal to have. And you look at the tar content, again, you have, well, updraft has higher, but nevertheless, compared to downdraft, fluidized beds will have higher tar content. That means you have to use an external device to remove those if you want to use the gas in a gas turbine. So these are the the end use. If you're burning it, it's okay. It could be large. Sorry, where did it go? If it's an internal combustion engine, you will be putting big holes in your pistons. If it's above this lit, gas turbines, as you see, much smaller. Same with compressors and fuel cells. It says very low, but I have spent the last maybe 15, 20 years of my research incorporating solid oxide fuel cells in my labs. And I tell you, there's zero tolerance in fuel cells for any particulate matter. In that matter, of course, very little tolerance to carbon. Otherwise, you'll be poisoning the cells. It is desirable to use the produced gas, of course, in the form of methane as opposed to hydrogen, but it has to be very clean to have the combination of gasifier and a solid oxide fuel cell. As I mentioned, heating value of a producer gas is relatively low, about 5 megajoules per cubic meters, and you compare it to natural gas, it is significantly lower than from natural gas. But natural gas, you have to have natural gas transported from wherever the well is to the end use, whereas the gasifiers can be built where the need is closer to the fuel. Therefore, you don't need to transport the fuel on long distances. Because of the almost unavoidable presence of tarry products, particulates, and ash, producer gas is generally dirty. The amounts of these undesirable products in producer gas can, however, be controlled depending on the design of the gasifier, the type, physical properties, and chemical composition of the feedstock, and the operating conditions of the gasifier. So, producer gas is additionally toxic because of its high carbon monoxide content. So if you have to make sure that it is in a completely sealed, closed loop Otherwise, of course, if it's released into the environment, it's toxic. If it's released in the plant, it is also toxic. If the fuel feed rate is lower than between 35 to 40 gigajoules per hour, that means approximately, it's a very rough estimation, about 2 tons per hour of dry biomass. Then fluidized beds are in general more expensive. So it has to be more than this amount. And it is, regardless of that, the most expensive part of the cost of the fluidized bed, it's the blower, which are very, very expensive, and also the main source of failure, the system. And therefore, the initial cost, infrastructure cost of fluidized bed will become very expensive if you're not able to feed a large amounts higher than 2 tons an hour. This is the industry standard. I should again give you another example. Many years ago, in the province that I live in, called Ontario, the government of Ontario decided that it will stop burning fossil fuels in its power plants. There were several coal-fired power plants, and I was part of a team that they asked to convert these coal-fired power plants to biomass-fired power plants. This was the power plant in question was about 270 megawatt thermal power plant. It was hungry for fuel, and quite soon the plant ran out of biomass, which was in this case wood, and they had to truck wood from other provinces, other places, so that they could feed that hungry power plant to show the public that, hey, we are being very environmentally conscious. See, we converted fossil fuel to biomass, whereas trucking all the biomass introduced a lot more carbon dioxide into the environment than the coal-fired power plant would have. Don't get me wrong, I am very much in favor of renewables and any kind of solutions that will minimize carbon dioxide and any environmental aspects. But in our, however, treatment of power production, we have to be also very realistic to understand the limitations. Yeah, we know that bubbling fluidized beds were the first designs. So I mentioned if we are using the gasifier for the purpose of combined cycle, but predominantly for power plants, then it is a lot better to ensure that it is pressurized. And it has incredible advantages. For example, the heat transfer rate in pressurized fluidized bed compared to the atmospheric pressure one is 4 times higher for the same fuel throughput. So it is incredible. Therefore, the size of a pressurized bed is 4 times smaller than an atmospheric pressure one for the same throughput. Incredible. I mean, you pay, of course, is significantly to pressurize it and the vessel walls and everything, but nevertheless, it's a much smaller geometry. So this is the part that we talked about whether internal or external heating will take place. I go back to the basics, fundamentals, that in order to gasify successfully, you need to pyrolyze successfully. To be able to do that, you have to ensure that there is not enough oxygen, okay, for the fuel to oxidize. So part of your fuel, at least, part of it is burning, giving you the exothermic reaction energy, but part of it is starved for oxygen, and it is there. However, you also need to control the temperature. In all our experiments, okay, the temperature control was significantly difficult. It is not like a car engine, you press the accelerator, goes. It's the fluidized beds have very high thermal inertia, and therefore you still need to adjust the gas, in this case, fuel, to control the temperature, but in the meantime, you increase the air amount through mostly secondary zones to make sure that you control the temperature. So it's a balance, very delicate balance. You adjust one, you adjust the other one. Finally, you find the right amount to bring it to steady state operation. In general, the operating temperature within the fluid bed is between 8 to 900. As I said, 900. My designs are always around 850 Celsius, well below the fusion temperature of most types of ash, and thus, except in cereal straw, had much lower fusion temperature or melting temperature that we had to operate the bed almost 650, 700, not above that. And thus slag and clinker formation agglomeration can be avoided. And high ash content, low density fuels such as rice ash can be gasified much more satisfactorily if you keep the temperature lower than these numbers. Finally, as I should state that the gas from a fluidized bed gasifier tends to have a high tar content. I showed it to you compared to the others, and lower operating temperatures. It is insufficient to crack the heavy hydrocarbons from the pyrolysis reaction. So you have some of it escaping the reactor. Therefore, puts a heavy demand on the cleaning equipment because those heavy hydrocarbons are in the form of tar. The gas additionally contains a large amount of unburned carbon particles, as well as the fly ash, ash originally contained in the fuel. Of course, because of the below ash fusion temperature in the bed, it comes with the product gas. So you have to remove them. As I said, the sequence of it is you put a cyclone separator. Cyclone is effective up to most 10 micron particles. If anything is below 10 micron, will escape cyclone, and then you have to have bag filters, electrostatic filters, and all of those to bring it down to 0.1 micron, if at all possible, to even smaller than feeding into a gas turbine. Even within the foregoing drawbacks on the fluidized bed gasifiers, they remain the favorite gasifier designs with researchers and commercial establishments. This is due to the fact that they are the only designs capable of adequately utilizing as feedstock, such as abundantly available agricultural residues, as rice husk, sawdust, cereal straw, and anything corn husk, which happen to be so difficult to gasify with other gasifier designs. This brings us to the end of our second hour. So students, I sent a list to Professor Sahoo to share with you. Those include some, they're all publicly, they were obtained from publicly open available sources. So there is no infringement on copyrights. They're all publicly available. There are three examples there I wanted to share with you. It's part of a tutorial of previous chapters, previous lectures, and some of it we may touch upon this one. And I would like you to go over them and solve those examples. They are solved, but work on it parallel with the video. It is similar to the example I shared with you yesterday. And then there is some videos on combustion and gasification. Please go over them and make sure you watch them before our lecture tomorrow. And I will spend the first 10-15 minutes answering your questions before we embark on the next topic, which is a fluidized bed drying. Okay, I will stop here, and I thank you for your attention and invite anybody who may have questions. Yes. The heat source is external. Yes. Yeah. Yeah. Yes. So think of this. Two in the direct one, you have one reactor. That reactor is functioning as a dryer, as pyrolyzer, as gasifier, and a combustor at the same time. Okay. Uh, it's in a way, so think of it this way. For 1 mole of fuel, I provide less energy, less air for it to be fully oxidized. So part of it is being oxidized, but the other is not. The part that is not being oxidized is going through pyrolysis. It's devolatilizing and it is gasifying. Okay, where is it taken its energy from? It's taken it from the combustion process of the part that I've provided enough oxygen. This is happening within the same reactor. The other one is you have an external combustor this time. The combustor is burning directly. I provide the combustor with excess air. It's above stoichiometry, and it is directly burning the fuel, producing heat, and then what I do, I take the inert bed material, okay, from that and feed it into a gasifier. That is my heat source. So that's the difference between the two, okay? One is direct, the other one is indirect. Yeah. Yes. Mhm. Yeah. Yeah. So it's all about a heating rate, okay? If you're doing it slowly, and you will say, what's the difference between slow and fast? There is no like rigid boundaries. It all depends on the kind of feedstock you're using. But regardless of that, and the only way you can determine that is through a pilot facility. That if your heating rate is rapid, you don't allow for heavy hydrocarbons, tar, okay, to form. It's produced, and you look after it later on. Like it is a smaller amount, much smaller amount. But if the heating is slow, the tar has enough time to form. So it's just basically you don't you devolatilize it at the same time. There's not enough time for a tar to form. So that is the thing. But of course, um, how do you provide that fast heating, rapid heating? It all depends on how much either within the reactor you will be burning or how much external you'll be providing. So it is not as simple as it sounds. It is externally very difficult to control. So if that was possible, we could completely avoid tar formation, but we cannot. So because we can't do that kind of rapid heating unless I use a third fuel source like natural gas or something I'm burning externally, which hurts the economics of the whole process, of course. You're welcome. I like it that you're very curious. It's you have to be very curious to learn better. Good morning to you. Tell me, say it again, please. Plasma gas. Did I hear you correct? You said plasma. Yeah. This is a completely different technology. Okay. Um, that we have much higher temperatures and resulting in uh, very high level of throughput, but it's a very different technology than some places they use plasma technology. It is not fully developed, but basically um, the temperatures are so high that you can reduce 20 garbage bags into the size of one tennis ball. But its operating principle is very different, and it is a lot more expensive to build, and it is laden with a lot of operational difficulties. That's all I know. I don't have any operational experience with plasma. Uh, the municipalities that consider this, they ended up using either downdraft or fluidized bed gasifiers. Okay.
हेलो 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 बंद कर दो।
हेलो हेलो ऑडिबल नहीं नहीं करी नहीं हाँ मैंने 3 मैंने ये मिताली अच्छी विदिशा अच्छी आउट आमर बीटेक पिला अच्छे राजदीप गणनायक 3rd year कौन शेयर तो हेलानी शेयर तो स्लाइड तो खुला अच्छे देखो हाँ देखो माइक स्क्रीन तो खुला अच्छी है हाँ शेयर स्क्रीन करते आउ थर कर स्टॉप शेयरिंग पुणी थर कर हाँ हो रहा था अच्छा ठीक है फिर से कर रही हूँ हाँ हाँ ओके you can write there please join we are going to start इको हाँ यस फुल स्क्रीन कर रहे हैं हेलो am I audible okay so today's good morning all participants today's presentation is on mixing and segregation in gas solid fluidized bed mixing and segregation are the fundamental operations fundamental phenomena for any fluidized bed operations so here the usually the people explain or the researchers work on the mechanism of the mixing in the fluidized bed operations whereas very less attention has been given on the techniques or the quantification of the mixing because the fluidized bed operations are whatever the phenomena have been considered that is or have been adopted for industrial applications or the whatever the assumptions they have made for the development of the model, that is assuming it is the fluidized bed is a dense phase, assuming the dense phase as the homogeneous fluid, and always consider the as the fluidized bed is a better or the excellent equipment for providing the uniform mixing. Although it is a general statement, this also needs the to be qualified or the quantified. So, in particular there is a dearth of the experimental results on the solid mixing in the large scale beds, that is with the gasification or the combustion or the drying. So, here what is the level of the mixing and what is the level of the segregation, that is not quantified, just overall it is stated that it is the uniform mixing takes place in the fluidized bed. So, here because of this, as it is the fundamental things based on the degree of the mixing and degree of the segregation, other phenomena is carried out. So, sometimes the efficiency of the other phenomena or other processes may be less because of these assumptions of the uniform mixing. In practice, whether it is uniform mixing is getting done in the reactor or in the fluidized bed or not, that very little work has been done on this. So, usually solid mixing which are combined with the gas flow analysis and the reaction mechanism provides the basis for the designing of the any commercial fluidized bed reactor. And bubbling fluidized beds which we have discussed in the last two classes, it is the mainly the fluidization is carried out because of the bubble formation, and where the bubbling bubble formation occurs because a mixture of the particles or the powders which may be of the different sizes, different densities, different shapes. So, they are taken in the fluidized bed, whether it is the reactor, gasifier, combustor. So, always it is not a single size or the single particle is taken. So, mixture of particle is taken. So, as particles are of the different particles are having different physical properties, they also exhibit so non-uniformity during the fluidization process, specifically in the when they move vertically in the upward flow, there might be some non-uniformity. So, that is why if fluidized beds are we consider on the basis of the assumption of the uniform mixing characteristics, solid mixing is often incomplete when particles of the different properties are present. So, that is why knowledge on this degree of the mixing, degree of the separations or the segregations are required to be known, and which we will be just focusing here. Some research works in our laboratory which was carried out, and for uniform, so that if proper mixing is done or the proper separation is done, accordingly the product will be of the required quality, and where we can that is decide what type of the, if it is properly mixed, what type what will be the probable efficiency of the next operations, and what will be the product quality. So, here whenever fluidized bed particles vary in the size or density, they usually they tend to segregate in the vertical direction. As I told, in the vertical directions non-uniformity is resulted because of the different physical properties. So, if less means particles having the low density or the lower density or the smaller in size, usually termed as the in the bed mixture of the bed particles, where the if you consider the low density particles or the smaller particles, they called as the flotsam, the higher density the heavier particles, and the larger particles that is size wise, they are called as the jetsam particles. So, these technical terms flotsam whose float means they remain in the top, and jetsam means they are remaining in the lower region of the bed. So here sometimes even if they having the that is degree of segregation, or there is some non-uniformity in the fluidized bed. So if you increase the superficial gas velocity, if we can provide the turbulent mixing, we may that is prevent, or we may avoid this non-uniformity to some extent, but always turbulent mixing is not required. That depends on the type of the material we are handling, because turbulent mixing means there will be attrition of the another problem may arise, that is attrition of the particles will be there, erosion of the internals will be there. So that's why depending on the requirement, if they are very strong particles, they are not likely to break with the force of the fluid. So then we may provide the turbulent fluidization by increasing the superficial velocity. So thus unless we know the only we know the size and the density or the shape, from that we cannot say whether turbulent mixing will be better or not. So we have to see the other characteristics. So that's why if we do not know, or we do not know the degree of mixing, degree of segregation, that may affect the fluidization process. So with the literatures, it was just various researchers have worked on this. They found out that degree of mixing and degree of segregation also, with the sense that local means local composition is whether it is corresponding to the overall composition of the bed or not, means local means at any particular portion, at any particular height, what is the concentration of the bed and what is the average concentration of the bed. That is the whether they are same or different. If it is same, that naturally the uniform mixing is there. If it is of the different, it is usually found that it is different. Although considered as the fluidized bed is provides the uniform mixing, but when we carry out the experiment, we find that the concentration in the local concentration is not match, do not match or does not match with the overall concentration. So segregation, in that case segregation occurs. So segregation occurs means there is substantial difference in the drag of the drag force exerted by the fluid on the particle and the unit weight of the particles, because if the there will be balance, then the particles will be in the fluidized state. Drag means fluid which is applying the force on the particles, that drag force, and it is the gravitational force of the particles. If they balance, the particles will be in the suspended state, and that will be in the proper normal fluidized condition. Now if there is the difference, naturally if the some particles, if the drag force is more, the particles will be dragged towards the distributor region, that is bottom region. If the it will be in the upper region. If gravitational force is more, it will be brought down to the bottom of the distributor. So thus in this way, if there is no balance, the particles are the larger or denser particles will be remaining on the bottom region, and they are be reluctant to mix. So there will be no proper mixing. So particles with the different density sizes usually fluidized, when fluidized, they tend to segregate. So this is the you found in the both liquid solid fluidized bed or the gas solid fluidized bed also. So this problem, if segregation will be there, particle size wise or the density wise, naturally it will be leading to the defluidization in the bottom of the bed. Means in the top region only fluidization will be there, the entire bed mass will not be fluidized, some dead zone will be created, means bottom corners some materials will be remaining as it is. As a result, the required quality will not be available with the product, and downtime the downtime will be the process downtime will be also difficult and the costly also. So on this way sometimes segregation is also required, that is suppose if you want to take out the product at some intermediate level, the particulate product and with respect to particular size or the particular density, then segregation will be utilized and can be brought to collect somewhere in the bed and to be withdrawn preferentially. And sometimes segregation also means, that is why the segregation can be used for the waste treatment and dry solid separation and for the classification of the that is solids in the wherever we are need in the waste management or the mass transfer. So thus segregation can be can play a role for the solid waste management. Now here if you see that there is the in the research, through the various research works, we find that dynamics of the mixed and the segregated fluidized beds are categorized based on the research work, that is researchers worked on the mixing or the mechanism of the mixing and the segregation, quantification of the mixing, that is mixing index concept, segregation intensity, segregation distance, and other related findings with respect to bed dynamics and effect of the baffles and the distribution on the mixing and the segregation. Now out of these 5 topics, here we will be focusing based on the research work conducted in our laboratory, that is on the mixing index, segregation distance in the fluidized bed with the use of the baffles or the promoters. Baffles means which offer some baffles or the promoters are used which offer some resistance to the fluidization process, that is some in the vertical direction, some in the horizontal direction, so that we can know that whether it is affecting the rate of segregation or the rate of mixing or not. So here the this mixing and the segregation, they can occur simultaneously to produce the equilibrium distribution, and also that is which is essentially uniform in a horizontal plane, but generally varies with the bed height, because sometimes in the bottom region there will be segregation, in the top region there will be mixing. That is why in the horizontal plane the concentration for all the particles will be same, but when we move from the in the vertical direction, the concentration will be different. That means there will be segregation in vertically. So both in processes are influenced solely and entirely by the bubbles. This is because of the bubble formation. So in the bubbles might be in the lower region, the bubbles, small bubbles will be forming, and they might be moving through the void spaces among the solid particles, and when they reach the upper region, bubbles may grow in size by coalescing with the other bubbles. As a result, there will be more bubbles in the top region than the bottom regions. So if you see the researchers Neimer and others, they developed expression for the mixing index, that is x star by average of the x bed, that is it is the x star means in the local level at any particular height the concentration of the particles, that is with respect to jet sum or the float sum, and x bed x bar for the bed means it is the average bed concentration, how much float sum or the jet sum are present in the bed, that is on the mixing index. And this expression was used in our lab to calculate the mixing index experimentally. Then correlations were developed, and it was compared with the experimental values. Here other researchers also worked on this mixing index, the quantification of the mixing. When there is Roy and others, they used the nearly spherical particles and in the different two-dimensional and also two-dimensional as well as cylindrical bed, that means two-dimensional and three-dimensional bed. And equilibrium, the composition of the bed was found to be function of the height, that and following correlations were developed, functions of the velocity, and here the as a function of height was measured as the following correlations were developed. When the size difference is considered, x, that is the it is the for the one particular particles, that is whether it is the flotsam or jetsam, it is measured as the function of the u minus uf into dj by df, that is for the size difference. Is the diameter of the jetsam, it is the diameter of the particle size for the flotsam, j subscript for the jetsam, f subscript for the flotsam to the power minus 1 by 5. For density difference, it is x equal to k into u minus uf and into rho j by rho f. Here density ratios of the densities for the jetsam and the flotsam raised to minus 2.5. From both the expressions we can see, here k is the proportionality constant, and you can see in the first size difference it is the function of the velocity difference. So both the expressions shows that the height of the or the height up to which the particles is moving, that is function of the velocity also, means it dependent on the velocity. And here also from both these expressions we can see that the for the ratio of the sizes of the jetsam and flotsam is raised to minus 1.5, that is minus 0.2. So that means here as coefficient is less, it's the effect of the size difference on the degree of the mixing is less in comparison with the that is effect of the densities, because here density ratio is raised to minus 2.5. So as here index is higher than this, so that means the degree of mixing is here inversely proportional, in minus sign is there, that means more separation will be there, mixing will be less. And here the only the magnitude wise if you see, the size difference has less impact than the density difference. Here both, as I told, it depends, both mixing and segregation depends very much on the velocity, and thus when there is more jetsam particles are there in the upper region, that means higher larger size or the denser particles move to the upper region, then the expression, that is the distance which the particle travels, it is expressed as the function of the u minus uf into size ratio of the jetsam to flotsam raised to the power minus 1.1 by 5 into density ratio of the density of the jetsam and flotsam raised to the power minus 2.5. If it is combination of the size and the density is taken, depending if the higher denser particles, larger particles are in the upper region of the bed. So thus here main effect of the size also, if you will see the, and hydrodynamics also is, it is also told that the minimum fluidization velocity is affected by the particle size. So that is main effect is the particle size for the which affects the minimum fluidization velocity, and the difference alone leads to very little segregation. So although the minimum fluidization velocity varies with the size, but it has little impact for the segregation. And other that is Duigen and Rietma, that is researchers also have developed the model for the mechanism of the mixing segregation in the homogeneous fluidized bed, and thus they observed that they concluded that the same theory is applicable for both liquid solid fluidized bed, gas solid fluidized bed, and which means anywhere in the bed the pressure gradient is proportional to minus rho bar g, where rho bar is the average density of the bed and it is the gravitational constant, and this is the pressure gradient. So, whether it is liquid solid fluidized bed or the gas solid fluidized bed. Now, some other researchers also worked on the quantification of the mixing index concept, where they found out that Uj by Uf, they developed the if there is the complete mixing of the two particles, then both the components have the identical terminal velocity, because as we discussed sometimes, I told in the previous classes, the particles which moves up, because it's here the drag force exceeds the velocity, exceeds the terminal velocity of the particles. If the terminal velocity of the particle is less, naturally it will be moving up. If the terminal velocity will be exceeding the superficial velocity, particle will fall down. So, if here when both the components in the mixture of the particles, if the two sizes are there, or two particles of the two different densities are there, they have the same terminal velocities, then we can have this Uj by Uf, that means velocity of the jet sum and velocity of the float sum will be same. So, that means here the ratio will be 1. So, thus we can say that here above and below this, this it is Uj by Uf 1 means it is the region of the perfect mixing. There is no segregation, because both jet sum, float sum having the same densities. So, this above and below this line of the perfect mixing, the degree of mixing will be 100%, below will be 0%. Above, because once we reach that critical level where the jet sum and float sum having the same velocities, same terminal velocity, above that the mixing will be 100%, below that it will be 0. So, that occurs in the upper region, because lower region means where more bed materials will be there. So, this will not occur, but in the upper region towards the freeboard region, so this may occur. So, we may find a point where both that is will be in the jet sum, float sum will be in the suspended conditions. That means that is the level of the mixing is that is the region where the level of mixing is 100%. Now, here according to this also, according to the same researchers, the segregation occurs at the lower porosities of the bed. As I told, in the upper region only we can get a region where the perfect mixing we can get, but in the lower region of the bed segregation will occur, because that is the region of the low porosities, means more solids will be there in the lower region of the bed having the lower porosities, because of which there will be segregations. And so, another researchers, Jena and others developed the correlation for the mixing in for index of uniform mixing in terms of the depth of penetration of the large float sum particles, how much it is moving in the particles moving for the circulation in the bed, as mentioned by the following correlations. So, this is just researchers and other researchers also developed that is what is the journey time, circulation time to journey time ratio for the particles, any particles whether float sum or the jet sum. Ratio of the circulation time to total journey time is function of the x by h, where x is for any particular time how much distance it is moving, whereas h will be the total distance available for its journey. So, then segregation, similarly segregation also quantified by the segregation intensity, segregation distance by some authors or researchers. Now, some researchers they have many researchers have concluded that if there is the size difference or the ratio of the jet sum to float sum is more than 1.3, segregation will occur. Similarly, if the volume fraction of the denser component exceeds 7% in the bed, then also the segregation occurs, and the criteria set by them was pointed out also this by Wakeman and Stubb. df by dj into rho f minus rho g by rho j minus rho g to the power half more than 1.13, where rho f is the density of the flotsam particles, rho j is the density of the jetsam particle, rho g is the gas, so the fluidizing medium. So gas solid, usually we take the air, otherwise if in the specific gaseous fluidizing medium is required to be taken, then rho g will be the density of that gas. So some empirical dimensionless segregation distance was also found out by Tanimoto and others. They expressed segregation distance, means how much distance there will be segregation in the bed. It was developed by Tanimoto and others, 0.6 into rho j by rho b into dj by db to the power 0.33, and Huffman and Rumpf modified this equation. It is 0.8 into rho j by rho bulk into dj by d bulk to the power 0.33 minus 0.8, where bulk means it is the entire and average density of the bed material, average size of the bed material d bulk, and j subscript the density of the jetsam and particle size of the jetsam. Now here C. Dexiri et al. Introduce some concentration term of the flotsam to calculate this segregation distance, and it is their expressions for the segregation distance is 0.8 into rho j dj to the power 0.33, Cf into rho f df to the power 0.33 plus 1 minus Cf into rho j dj to the power 0.33 minus 1, where Cf is the concentration of the flotsam and rho j dj are density and the particle size of the jetsam particles. And in our lab this equation was used to measure the segregation distance in the fluidized bed, and then the correlations were developed, and this is the value was taken to as the experimental values of the segregation distance. Later the calculated values were compared with the segregation experimental values, which we will be discussing later, just now after 2-3 slides. So here this equation was used to calculate the experimental values of the, that is it is the Wen and O correlations for the minimum fluidization velocity. There are actually in the Kuhn-Levenspol fluidization book many expressions are there to calculate the fluidization velocity, minimum fluidization velocity, but here the depending on the particle size, as in the in our lab it was the coarse size, usually Geldart AB sizes were handled, particles are handled, and we used this equation to calculate the minimum fluidization velocity. And some more researchers also they concluded that there is always, although it is true also, that there will be some upflow of the solids and will be downflow of the solids during fluidization, as it is a continuous process. During fluidization, with the force of the fluid, some fluids are going up, and when the terminal velocity of the particle exceeds the velocity of the fluid, the particles will fall down. That means it will be continuous process, some particles moving up, some particles coming down. So thus and during the upward movement, downward movement, there is the that is interchange between the streams also, upstream and downstream. There will be interchange of the some particles also. So that because of that also mixing takes place. So Van Dimter divided these solids into 2 streams, and also in a tall enough bed of the solid particles, and developed the 2 models, that is for the upflowing solids they developed this expression, for downflowing solids developed this, which is concentration CSU, concentration of the upflowing solids CSD, concentration of the downstream solids, and here the fraction of the solids in the upflow, fraction of the solids in the U subscript for the upflow, D subscript for the downflow, and here the it is the interchange coefficient Ks, and thus he developed the researchers developed this correlation for upflow and downflow solids. And some fast bubbles, as yesterday we are discussing in the fluidized bed catalytic reactors, if the UBR is much larger than the UF, that is bubble rise velocity is larger than the superficial velocity of the fluid. In that case, what happens? Bubble moves faster. After moving certain distance, bubbles breaks. When the bubble breaks, naturally some solid particles which will be within the bubble, and the solids which are carried over with the cloud, that is the wake, cloud wake. When the bubble breaks, these solid particles scattered in the horizontal directions. That is why it is the dispersion, means they dispersed in radially. So, this dispersion coefficient was developed by the these researchers as 3/16 into del f delta f by 1 minus delta f into alpha square UMF dB by epsilon mf. Actually, using this reference, one mathematical model was also developed in the in our laboratory research work. So, again fluidizability. So far we discussed that how mixing quantified and segregation quantified. Now fluidizability also, there is another term, fluidization index also. Now to know that whether proper fluidization is taking place or not, proper fluidization means the solid particles are fully supported by the gas stream. That solid particles in the suspended form means it will be moving up and down, but in the suspended form, not coming down to the bottom of the bed, or neither entirely remaining in the freeboard region. So, if they are fully supported in the gas stream, the bed pressure drop will be equal to the weight divided by the cross sectional area. That is, fluidization index is measured delta P by W by A, where W is the weight of the bed, means total bed materials whatever taken its weight, and area is the cross sectional area of the bed. So, if the fluidization index will be close to unit, we can say that it is the ideal fluidization is taking place. And this what happens here, if the fluidization is not ideal, or it is fluidization index is not close to unit, that means proper fluidization is not taking place. In that case, as yesterday we discussed, gilded C particles, where the cohesive particles are there, that the force of attraction, cohesive force is higher. So, they will not be easy to there will not be fluidized at all. So, in that case, to break these interparticle bonds and improve the quality of the fluidization, we may provide some stirring or the vibration, because of which the fluidizability may improve also. Now, the variables which affect the segregation, that is required to be, before quantifying the segregation, we need to know the variables, what are the variables affecting the mixing and the segregations. So, the based on the research works which have already reported by the researchers, it is observed that bed aspect ratio, as in the reactor also we discussed, the bed aspect ratio height to diameter is the important aspect or important parameter for the proper fluidization. And so, that means how much material we can take in the bed also, based on this aspect ratio can be decided. Then weight ratio for the segregating components in the bed. What suppose larger size and smaller size you are taking, or the denser particles and lesser denser particles, less denser particles you are taking, some what ratio should be taken. It is not that more 90% more higher density particles you are taking, 10% only the low density we are taking. So, then it will be difficult to fluidize. Similarly, the for the size difference also, so there should be some weight ratio of these two components, jetsam and flotsam. And then the critical bed diameter at which the segregation will be 0, 100% mixing will be obtained. Similarly, properties of the fluidized bed systems which are independent of the particle properties. So, as a whole, what will be the properties of the fluidized bed system, means in combination of the fluidizing medium, that is the gas and the solid, that is the fluidized bed system, and with the arrangement of the internals. So, that also to be known beforehand, so that we can know what will be the quantity of the mixing or the segregation. And fluidized bed dimensions such as bed diameter and height, this is giving the, although height here aspect ratio we are calculating again exactly, because with different values we may get the different values of the height, different values of the diameter, we may get the same aspect ratio, but their height and diameter we should determine properly, means that is in the design. And the bed operating conditions such as how much superficial gas velocity to be, at what velocity we should provide, so that it will be the fluidization velocity will be 2 to 3 times the minimum fluidization velocity, means it should not exceed 5 times the minimum fluidization velocity. So, where we should place the baffles, distributors, that is internals, and distributor, the holes, so how the holes to be arranged, what will be the pitch, and so all these also affect the quantity of the or the quality of the mixing and the segregation. So, thus if you critically analyze all these literatures, it is found that investigations are there relating to fluidization quality, mixing index, segregation distance, segregation index, fluidization index, extent of segregation, distribution of jetsam particles, all have been there in the cylindrical 2-dimensional or 3-dimensional fluidized bed, with or without the use of the promoters already there. Almost all have tried to analyze this distribution of the jetsam particles in the fluidized bed. What they do, they have done, as per the literature we find that they fluidize the bed for some time, then stop the air supply, that means bring down the bed materials to the static condition, then they analyze what is the distribution of the jetsam. But during the fluidization, what is the distribution, that was not reported in the literatures. So, that is why in our lab we tried to focus on this, that is during the fluidization what is the distribution of the jetsam and the flotsam in the bed. So, although these investigators have thrown some light on the mixing and the segregation characteristics, and definite conclusions are not made by them regarding the characteristics of the materials with or without the use of the promoters in the fluidized bed, promoters which enhances the quality of the fluidization. So, there is limited literatures on the quantitative study on the effect of the promoters related parameters for the fluidization, that is concentration of the jetsam particle in different layers of the bed, thereby the mixing index, segregation distance, and the minimum fluidization quality also. So, based on this, so here in the laboratory we tried to conduct the experiment using the promoters and decide the or determine the jetsam distribution in the bed in the static condition as well as in the fluidized bed conditions. That is static condition means fluidizing for some time, then shutting down, bringing down the particles to the static condition. fluidizing conditions means during the fluidization some samples are withdrawn and the analyzed also the concentration of the ZSAM, and all these results were means correlations were developed and compared with each other. So that is unpromoted how the experiments were conducted. Two promoters were used, figure I will just show, and experiments were carried out in 4 types, that is static bed conditions. The bed was made static by stopping the air supply completely after fluidizing for some time, then unpromoted fluidized bed during the fluidization without using the promoters, then fluidized bed with the rod promoter, fluidized bed with the disc promoter. So here the materials were in the static condition, materials taken layer wise, that diagram I will show. So how the through the side ports during fluidization materials were collected in the side ports. This was the experimental setup with the gas solid system where the that is solid particles of the different size mixture and density mixtures were taken, and air was supplied through the compressor and the experiments were conducted. During fluidization, the here from the side the samples were collected at different levels to find out the concentration of the ZSAM at different levels, and in the static conditions, that is after fluidization when it was shut down and the materials were brought down to the static conditions, the layer wise samples were collected from the top. So this is diagram will show promoters we have used in the laboratory, that is rod disc promoters. Here this is the rod promoters. Disc promoter, that is circular discs made up of the perspex sheet. A number of holes are made here, and for the air supply, and the central hole, this is it is a central rod is there to carry to hold number of discs at regular distance of the 5 centimeter. Number of discs were provided. Here rod promoter, number of this here about 8 rods were just here 4 inside. They are arranged to give in one circular path. Here another 4 were there outside circle also, means thus 8 rods, and another central rod is there. All these were welded to a ring shape is there in the top. 2 ring shape are there. These 4 rods welded to the inner circle and the inner ring, and the 4 rods were welded to the outer ring. So rod promoter, this gives the that is as it is positioned, and it offers the resistance in the horizontal directions, and when this is positioned, this as discs are there, they offer resistance in the vertical direction, means obstruct the movement of the particles in the upward directions. As I told, in the static conditions materials were collected layer wise. Here this is the fluidized bed, and a top plate is given where the hole is made, and here the aluminum tube is given, and here the vacuum is with the vacuum it is samples is collected layer wise. From the top it will be collected, it's again it will be size distribution, concentration of the ZSAM will be measured, then another layer will be collected. So layer wise with the vacuum, by sliding this plate over this column, we can just we collected the samples layer wise. So then rotameter was calibrated, because airflow when in the experimental setup here rotameter was used, number 5. The rotameter is used to measure the flow rate of the, so it was calibrated first. Then the experiments were conducted. First hydrodynamic study with the for the with this during this hydrodynamic study we measured the that is minimum fluidization velocity, that means measure the pressure drop by varying the velocity, and where we studied the effect of the particle size, if bed height, and here the compositions, means when the size mixture or the density mixtures we have taken, in what proportions we prepared the these mixtures. So, here we can see it is for the homogeneous binary mixture. Here we have referred homogeneous means that is the same density, different sizes we have taken, where diameter particle size ratio is 1.4, 1.78, 1.986. That means different sizes are there, and fine size we kept constant, only larger size we varied. So, here we found all the here, and here also we compared all in the same trend here by varying the bed height. The third plot we got, that is 10:90 ratio, the larger to smaller size mixture, then 25:75, 40:60, 50:50. So, this was studied, and it was observed that minimum fluidization velocity following the same trend, and but it is found that you can see here the 10:90, it was initially showing 10:90 means larger size is the 10, 90 is the smaller size. Initially it was showing the higher velocity, means increasing, then finally it was 40 to 60% mixture was giving the higher velocity, means this pressure drop, and here that is also in the triangle shape it is there, it is giving the higher pressure drop. That means here the minimum fluidization velocity is higher here, because we can say that this is the critical mixture where we can have the better fluidization. So, similarly for the homogeneous binary, sorry, this is for the heterogeneous, not the homogeneous, because density ratio we have taken, here title I have kept the same. So, heterogeneous, here density ratio we have taken, we have studied here the bed height, effect of the bed height, here effect of the compositions, 10:90, 25:75, 40:60, 50:50. From here we can see that here 10:90, where the less jetsam particles, means dense particles are there, there we can say it was starting from the having the less density, less pressure drop, and finally its pressure, means it fluidizes properly, and its fluidization velocity slightly more than that, almost having the same for the 10:90, and here 50:50 is having the here this once fluidized, and it is having the reaching the minimum fluidization early, means less minimum fluidization velocity. Here we can see for heterogeneous. So, when the density ratio we can see here, density ratio when it is 1.4:4, that means it is the not the 1.87, it is the fluidization velocity is coming higher for the density ratio 1.404. So, that means you can say that this is the critical mixture ratio with which we are getting the higher minimum fluidization velocity. Then properties of the materials, that is size wise, as I told, different sizes we are taking, size mixtures. So, here smaller size we have kept same 0.725, larger size we have varied 1.015, 1.4, 1 have taken. Here you can see size of the jetsam, means first keeping the, it is for developing the correlation or the carrying out the experiment, one parameter is varied at a time. Here we can see that that is average particle size, how it is for the first 4 it is remaining same, and initial static bed is varied here. Now, then the so similarly you can see that proportion is varying here 10:90, 40:60, 50:50. So, here it is kept constant, that is bed height is kept constant. So, this way the correlations and it is the heights of the layers for the withdrawal of the samples, means each 2 centimeter was collected from the bed by vacuum, that is layer wise was collected. Thus, the correlations were developed. Here we took the developed the on the basis of the dimension less or the regression analysis. It is the dimensionless, as it is the mixing index. Index is a number. So, here also we took the dimensionless groups, HS by DC means aspect ratio, and that is they have also taken the that is concentration of the jetsam, but here we that equation we used to determine the experimental values of the segregation distance. Then we developed the correlations by considering the all these parameters, HS by DC, HB by DC and U0 by UMF, and here the jetsam float sum size ratio multiplied with the mean size and the float sum size ratio. So, thus we got the correlations for the different conditions. Similarly, for segregation for the heterogeneous binary mixture also we developed, and in the previous it was df by dj, here rho f by rho j. So, we are taking, and correlation plots, just sample plots I have shown here, how the different parameters we have taken showing that effect. We have developed these correlations, and correlation plot for the heterogeneous mixture, and similarly this is the correlation plot for the segregation distance for the homogeneous mixture, and this is the correlation plot for the segregation distance for heterogeneous mixture. And for the homogeneous mixture, model was developed, I have not reported here, but that was model to compare the theoretical model data with the calculated values obtained from the through these correlations. Then for the segregation distance, ANN was used, this was the optimum structure, and to find out the values of the segregation distance, and the sigmoidal activation function which was used for ANN analysis was fx is 2 into 1 by 1 plus e to the power minus lambda x minus 0.5. This activation function was used to have the training of the data. So, thus correlations were developed using the ANN also, similar type of the correlations, then it was compared. Now, for the when we compared with the ANN data with the dimensional analysis approach and the ANN approach, standard deviations and the for the static bed conditions, unpromoted fluidized bed and the rod promoted fluidized bed, disc promoted fluidized bed, 4 conditions it was fluidization was taking place. So, all the cases we found that standard deviation, mean deviations are in the just below the 10 it is there. So, from this we can conclude that here also for the homogeneous heterogeneous mixture also we here only just unpromoted bed only this here standard deviation slightly more than the 10. So, thus we can say that these comparisons is gives that the developed correlations are applicable or can be used over a wide range of parameters which gives the or which quantify the segregation of the particles as well as also the mixing of the particles. So, here when we use the 4 conditions, 4 bed fluidization conditions to determine the quantify the mixing index, segregation index. So, these data or these correlations can be used to give the prior information about the degree of mixing, degree of segregation, based on which the next process, that is fluidization, fluidized bed reactor the reaction, whether what type of the reaction can be, whether plug flow or the mixed flow or the fluidized bed drying, gasification, all can also be that way can be modified, or their efficiency can be improved with these informations. And here degree of mixing is very from this through these experiments it was found that degree of mixing depends very much on the gas velocity. Even strongly segregating systems can either be separated or well mixed by controlling the superficial velocity. So, new lights also has been thrown on the significance and the magnitude of the different parameters, that is initial static bed height, height of the layer of the particles HB, which I just told, above the bottom grid, superficial gas velocity, minimum fluidization velocity, average particle size of the mixtures, which are also included in the development of the correlation for the mixing and the mixing index and the segregation distance. And here the Geldart BD particles were selected. So, we can apply these correlations for the Geldart B particles or the Geldart D particles alone also we may apply with slight modifications. And here during the segregation, following points were observed, that is segregation by size difference appears to be intrinsic feature of the large particle beds. It becomes larger as the size of the fine decreases, the mean size of the bed solid increases, the gas velocity approaches minimum fluidization velocity. And also when segregation occurs in the bed of the small amount of the denser particles, if jetsam particle is less percentage, the near the distributor only the jetsam will be richer or concentration will be high, then remainder bed has a fairly constant concentration, means uniform concentration in the rest of the bed. So, in segregation size difference, segregation by size difference, the concentration of the fine or the coarse appears to be vary rather more uniformly than the that is denser particles. If the size difference in the density we consider for the bed mixtures. So, thus we can also conclude that that is downward relative displacement velocity of the jetsam particles in the emulsion phase as found to increase with the excess or with the increase in the fluidizing velocity, but it is dependent on the depth of the bottom stratum. So, thus it is also observed that both mixing and segregations are affected by the or hindered by the baffles. By using the promoters, the rate is affected. So, baffle or promoters which in the vertical plane hinders the segregation, but improves the mixing process. Using these promoters we can get the better mixing, as we discussed also, that is using the vibration or the stirring we can use for the cohesive, we can break the cohesive forces for the Geldart C particles. So, thus using these promoters we can have the better mixing, whereas the horizontal promoters hinder the mixing, improve the segregation, because horizontal promoters obstruct the vertical movement of the upward movement of the solids. So, thus horizontal promoters improves the segregations. So, thus knowing this mixing and the segregation or the indexes, and we can quantify the level of the mixing, level of the segregation, then we can use for the waste management, solid waste management, and the separation of the any particular quality or the particular size or the density during the fluidization process. So, size separation or the in the drying process also we can separate out a particular level product can be drawn at a different level of the time. So, thus we can use this for the maintaining the sustainable. It is the, although directly it is the solid waste management, we can use this, and other processes it is the fundamental approach to have the information, prior information on this, based on which the efficiency of the gasifier combustor reactors can be improved further. So, thus it will indirectly help in maintaining a sustainable environment. So, thank you. Any questions?
यहाँ पे होगा तो माइक ये करेगा, आवाज मैडम का माइक ऑफ करते हैं। नहीं मैम पूछ रहे हैं ना, मैम के साथ कोई
No, on
कैमरा
everything.
कैमरा ले ले, कैमरा दोनों
If there is no questions, then okay.
how you ask where it will be recorded? बुझना तो इसको तो आदत है।
Actually, sir, এই মাইক রেকর্ডে হি আপন সুপার দিতে নহল
नहीं नहीं এটা मैडम को मतलब बते दो ना, मैडम को माइक का जस्ट खाली ऑफ ही जीव बोलता है मैसेज करी हो
Okay.
ସେଠି ବୋଲେ ଏଇଠୁ ରେକର୍ଡିଂ ରେ ଯାଉନି ନା,
और रिकॉर्डिंग में जीव
ନା
ना वो मैम
ଲାଇଭ ଷ୍ଟ୍ରିମିଂ ରେ ଯାଉନି।
मैम तो फिर एमएस टीम का कैसे होगा? वो तो एमएस टीम में कैप्चर होगा ना।
एमएस टीम में
कैप्चर हो जाएगा। कोई भी बोलेगा मैम का वहां से कर रहे हैं, ऑनलाइन में कोई आंसर देगा क्या? लेकिन मेरा ये भी आना चाहिए और मैं क्वेश्चन पूछ रहा हूँ वो भी आना चाहिए ना, दोनों चीज।
वो कैमरा इधर से कौन है, आप वो उस माइक में बोलिए, वो आ जाएगा।
This mic you can use.
आप वहां से बोलने से यहाँ से सुनाई देगा वो माइक में। Madam, one question I have. The promoters are good for the mixing, but as far as the segregation is concerned, it is not good for segregation as I understand. And another aspect of that, the particle erosion because of presence of the promoters will be there. So how to address all these things?
Thank you for the questions. See, promoters to enhance the mixing and the segregation, although simultaneously both the things not possible. For the mixing, the promoters, usually vertical promoters, help in the mixing. That is, during the fluidization there might be channeling or the uneven flow of the solids, non-uniform solids flow will be there in the vertical directions. So, if you use the vertical promoters, then it will nullify the non-uniformity and improve the uniformity of the solids and quality of the fluidization. As a result, mixing will be better. But for the segregation, we have to use the horizontal promoters. It may be a type of the sieves, means a series of the sieves if you use, or just in the present case we use the disc promoter and having the diameter that is slightly less than the column diameter. So, if you they are placed at a distance of the 5 centimeter, we have placed the discs. So, in this case within that 5 centimeter fluidization will be taking place in the lower 5 centimeter. So, that means the particles which are the less dense particles or the lower size particles, they will fluidize through the side of the promoters. Thus, it improves the segregations, that is heavier particles will remain in the lower portion of the bed and the lighter or the smaller size particles will move up, fluidize through the sides of the promoters. Thus, this disk promoter or any horizontal promoters will assist or will improve the segregation quality. That is one aspect. And the another questions, what are the questions?
Erosion.
Erosion, yes, that is erosion means when the segregation quality improves means only lighter or the smaller size particles will be moving up vertical direction through the sides of the that is promoters. Naturally, it is in the central region the obstruction is there if disk promoter is used. Through the sides only it is moving, so its velocity is less, and for which there will not be erosion, it will be just passing or the moving up through the there will not be any vigorous movement, moving slowly towards the top in the vertical direction, and there will not be any smooth flow will be there, there will not be any erosion or the collision of the particles also. So, thus it improves the quality of the segregation. Okay. Thank you. Any more question, online members? Okay. Thank you. Then we will stop here. So, next speaker will be Professor Jena. हाँ अभी करेंगे अरेंजमेंट को we are starting the next lecture within 5 minutes ऐसे लिख दीजिए नहीं ठीक है
अच्छा से मैडम पानी आने के लिए देखिए अच्छा तुम लोग स्टार्ट करने से मैं ज्वाइन करूँगा तो The screen is visible. This screen is coming. এটা কাহিଁକି ଆସିଛି ଏ ସ୍କ୍ରିନ୍ ଟା এটা କଣ ଆସିଲା ନା Dear participants, a very good afternoon. Am I audible? Am I audible? Okay. So dear participants, very good afternoon to one and all. I am going to discuss the topic semi-fluidized bed in waste management. The hydrodynamics perspective of this system I am going to discuss, which will help us in design the semi-fluidized bed system in waste management. So as you see, the semi-fluidized bed is a combination of a fluidized bed and a packed bed. But the packed bed is not at the bottom of the vessel, it is at the top of the vessel. When the free expansion of the fluidized bed is arrested by a top restraint screen, we get a packed bed at the top. As you know, initially when you are going to fluidize a bed of solid particles, you are allowing the fluid to move in the upward direction. As you increase the velocity of the fluid through the bed of solid particles, from the fixed bed, the particle at the minimum fluidization condition start to fluidize, and further increase in the fluid velocity, the bed expands. Bed expands means the particles are lifted to a greater height, and as you go on increasing the fluid velocity, the particles will get lifted to a greater height, and if you arrest the free expansion of the bed of solid particles by a top restraint, then your a packed bed is formed at the top of the bed, where a combination of a fluidized bed at the bottom and a packed bed at the top we get. In chemical process industries, we come across various solid fluid contact operations. In my previous lecture, we have discussed about different types of gas, liquid, solid contacting systems, and predominantly for the upward flow and the downward flow of the fluid, the fluid solid contact systems are primarily three types. One is the packed bed, primarily used till the Second World War. A packed bed means it is a bed of solid particles which is intact. Whatever the fluid velocity through the bed may be, the particles are not going to move. That means it is restricted by two restraint plates, one at the bottom and one at the top. As you see in the figure, it is a typical packed bed system, which is the upflow packed bed biofilm reactor in my laboratory. So through the perforated grid at the bottom, the fluid is allowed to flow in the upward direction, and the fluid moves through the void spaces between the particles. Those are in a closed packing. Then a fluidized bed, that top restraint is not there. The particles are not confined by two restricted plates. Rather, one side at the bottom there is a grid through which the fluid is flowing in the upward direction. So when the fluid velocity is sufficient to provide the drag that overcomes the net gravitational force on the particles come to a state of fluidization, and further increase in the fluid velocity, the particles move upward and the bed height increases. If you arrest the free expansion of this bed of solid particles by a top restraint, then you get a stationary particles of a packed bed at the top, and the bottom portion, the particles are in the fluidized condition. That means they will rise, again they will fall, back mixing of the fluids are there in the fluidized bed. So a top packed bed at the top and a bottom fluidized bed is nothing but a semi-fluidized bed, and that concept came in the late 50s, but which was in use late 80s. Two different systems. So as you see, it is one experimental photography view. Initially it is a fixed bed without fluidization. Then at certain liquid and gas velocity, the bed fluidized, and the fluidization is up to this height. This is the bed height. Initial static bed height was this. Now further increase in the fluid velocity. Now you see there is a top restraint here. So the particles are touching to the top restraint and it is confined there. So a packed bed is formed at the top, and this portion, the bottom portion, that is in the fluidized condition, and this portion is a packed bed is there. And if you further increase the liquid velocity and the gas velocity, then the height of the packed bed at the top increases, and the bottom portion, the fluidized that is in the fluidization, but the particle concentration is less because most of the particles are lifted to the top packed bed. Thus, the semi-fluidized bed is a combination of a batch fluidized bed at the bottom and a fixed bed at the top within a single vessel. The degree of semi-fluidization is the combination of a bottom fluidized bed and a top packed bed. Degree of semi-fluidization means how much of the solid will be in the fluidized bed portion and how much will be in the top packed bed portion, can be changed by varying the by varying the fluid velocity or by altering the position of the upper concentrating plate. So the conditions for the semi-fluidization are minimum semi-fluidization condition and maximum semi-fluidization condition. The minimum semi-fluidization condition is that the first particle of the expanded bed of the fluidization just touches the top restraint of the semi-fluidizer, and the maximum semi-fluidization velocity or the condition is that when all the solid particles of the bed are attached to the top restraint. There are certain advantages and disadvantages of the semi-fluidized bed system is there. So before going to discuss the advantages of the semi-fluidized bed system, let us see the disadvantages with the fluidized bed and the packed bed system. A fluidized bed system, there is a back mixing of the particles because the particles are in circulation, particle rise, then they fall. So this fall of the particle is because of the loss of the driving potential, and attrition and erosion of the particle because of the particle collisions are there. So particle attrition and erosion takes place, and if a high velocity for the fluid is used, then carryover of the fines because of erosion, fine particles may be generated, or it may be it is not that single size particles are fluidized, rather in a fluidized bed combustion system, as the coal is burnt, so the size of the coal gradually reduces. So as it becomes smaller, okay, for the same fluid velocity, the smaller size coal particles will be carried over. So for that, the carryover of the fines will be there, and as the carryover of the fines are there, then total this transportation disengaging height TDH should be provided. That means additional height should be provided in the bed, and or otherwise a recovery system should be there, like a circulating fluidized bed as it is discussed. So a circulating fluidized bed system can take care of this thing for particle circulation. Then certain disadvantages of the packed bed are the particle segregation, then local hotspot because of the non-uniformity of temperature if the reaction is carrying out. So all the area of the the bed of the solid particles, the liquids solid reaction or gas solid reaction are not to the same extent. Because of that, if some exothermic reaction is taking place, local hotspots are there. And the packed bed also, another disadvantage is the channeling of the fluid. So without touching the entire the solid particles in the bed, the liquid or the gas flows through some channels. So this can be avoided by the use of a semi-fluidized bed. Combination of the two phenomena, that is to have both the packed and fluidization conditions in the same setup, and choosing suitable parameters like the restraint position. The restraint position in a semi-fluidized bed can be varied. Just a minute. That's it. ये वाला मैं नहीं कर पा रहा हूँ, मुझे दिखाई नहीं रहा। इसका ये वाला आ रहा है मेरे में, इसको कैसे? लेकिन वो ही आ रहा है। Again, it is coming. इसको कैसे खोलना? नहीं हो रहा है. A little bit presentation issue. I am coming. अरे वहाँ पे देखने से मुझे तो प्रेजेंट करने में प्रॉब्लम हो रहा है ना, तो और तो कुछ है नहीं. ये क्या है?
प्रेजेंटर मोड में जाइए. सेटिंग. ये तो ऐड प्रॉब्लम नहीं होगा नॉर्मली कीजिए.
बट ये मूव भी नहीं कर रहा है ना. अखिलेश सर को जल्दी बुलाओ ना. Okay, let me continue. There is a little bit problem on this screen. So the fluid velocity to achieve, again I repeat, choosing suitable parameters like the top restant position and the fluid velocity to achieve different degrees of semi-fluidization. So this semi-fluidization partially eliminates the disadvantages of the fluidized bed, that is back mixing of solids, attrition of particles and erosion of the surfaces, and that of the packed beds, that is the non-uniform bed temperature, segregation of solids and channeling. Serve as a unique combination of back mix and tubular reactors in series. So bottom the fluidized bed is a back mix reactor and the top packed bed is a tubular reactor. And this is very good. Back mix reactor means it is a kind of CSTR and the top is a plug flow reactor. So CSTR followed by PFR. You know the significance of this combination, and this is best suitable for fast order reaction, for systems having fast order reaction. Few applications of certain applications. फिर आ जाना. नहीं आसना. अच्छा. Sorry for the disturbance. The applications: physical processes, drying of bean, squash seeds, high moisture potato slice, drying of garlic, pomegranate seeds, cantaloupe seeds, filtration of fine particles from liquid or gases, adsorption of trace organic compounds from water. Some amount of adsorption occurs in semi-fluidized beds at lower pressure drop than the fixed beds. That is the advantage. Filtration of fine hydrocarbon suspension present in the heavy gas oil fraction in the hydro desulfurization of bitumen derived crude. These are certain industrial applications, and some recent research on these physical processes are as you see in this table: drying of garlic seeds, drying of high moisture potato slices, drying of squash seeds, then high moisture fava bean drying, adsorption of aqueous phase divalent heavy metal ion removal of methylene blue, aqueous phase phenol removal from synthetic and real steel plant effluent, wastewater treatment with reference to steel plant pollutants. Then chemical processes, extraction reduction of iron ore, continuous coking of coal, boilers with semi-fluidized bed furnaces fired with low grade coal. Pyrolysis followed by combustion is used for high efficiency and environment friendly chain grade boilers. In ion exchange, removal of copper ions from electroplating wastewater. These are certain applications which is there in the industry already, and some of the research are like this: synthesis of lactic acid from molasses and cheese whey, chemical looping combustion process, gasification of spent coffee grounds using steam and carbon dioxide gasification medium, azodide removal from seawater by granular heterogeneous Fenton catalyst, natural iron ore as an oxygen carrier for denitrification in chemical looping processes. These are certain new research. Then in biochemical processes, in the extractive fermentation of ethanol, structured granule tablets formation, pediatric medicinal preparation consisting structural granules containing an extract of milk white iris. Then in the form of a bioreactor for aerobic wastewater degradation, novel bioreactor system for the treatment of palm oil mill effluent, aerobic treatment of distillery and petrochemical wastewater, synthesis of lactic acid from molasses and cheese whey, xanthan gum synthesis from dairy waste. These are some new research. So the importance of this semi-fluidized bed, as we see, that are physical processes, its applications are there, chemical processes and biochemical processes. I am taking the reference of the biochemical process, that is the bioreactor, because the most complicated operation is with the bioreactor. We are having the microorganisms, living microorganisms. So living systems are always the behavior is stochastic. To handle these things a little difficult. So fluidized bed bioreactors I am taking as the example. So these fluidized bed bioreactors are successfully applied in the treatment of several kinds of wastewater, we know, because these fluidized bed bioreactors are capable of achieving treatment in a low retention time, offer distinct mechanical advantages, allow small and high surface area media to be used for biomass growth. But the practical problem with the fluidized bed bioreactor is the excessive growth of the biomass on the support media. When excessive growth of the biomass on the support media is there, then the particle density decreases. So the particles float onto the top or rise to the greater height. And if it is fluidizing at low fluid velocity, this can lead to channeling of bioparticles in fluidized beds. The problem of overexpansion of the fluidized bed has generally been solved by the removal of heavily biomass laden particles from bioreactor, followed by the addition of biomass free particles. As the biomass grows on the particles, that becomes lighter, density decreases. So that move to a greater height, so that which is not suitable, and the bottom portion where the treatment, the contact should be more, that is does not happen. So the biomass laden particles are removed from the bioreactor and fresh particles are added. That is an inconvenient thing. Then complications is that introduces the need of additional equipment which is external to the bioreactor, that means a vibrating screen or an incinerator for the removal of the biomass from the particles. Again the particles can be recharged to the fluidized bed. So a semi-fluidized bed bioreactor is shown in this schematic. As one is a phenolic water. This in this tank the phenolic water is there. Then this phenolic water from the effluent, and it is a primary clarifier. This number 2 is the primary clarifier. 3 is the excess sludge is removed in this primary clarifier. 4 is the agitator. Then it is agitated, that means aeration is done to some extent. Then dilution tank is there where fresh water and nutrients are added. Then another then this water is charged to the vessel at the bottom and flow in the upward direction, and the biomass particles are there in the bed. Then air is allowed to flow in the upward direction. It is aerobic system, so aerobic phenolic wastewater treatment. Then this is your fluidized bed section, and at the top here it is the packed bed here, and above that this is the top restraint. This is the top restraint here. Above that a two-phase region, only the flow of the air bubbles are there and the liquid is there, and this is the disengagement section. Bottom section is the distributor section. It contains one air spurger here. So inside the bed, that is the main fluidized bed, that is immobilized culture on solid matrix is there. Then treated water is taken out from the disengagement section. The stages of operation of a semi-fluidized bed bioreactor: seeding of the bed by microorganisms and nutrients, that is wastewater, at flow rate slightly higher than the minimum fluidization velocity. That means the bed expands little above the static bed. Microorganisms grow in suspended phase and attach to available surfaces, that is column wall, and the fluidizing particle. The fluidizing particles may be sand, coal, other packing with a large surface area, maybe plastic beads, polystyrene beads, etc. When the fluidizing particles are coated with microorganisms, their size grows and become immobile, thus remaining stationary at a location fixed to the top restraint of the semi-fluidized bed. Thus a semi-fluidized bed becomes operational. So as microorganisms are coated on the particles, that becomes lighter, so that for the same velocity of the fluid, the particles move upward and touch the top restraint, and a top packed bed is formed. The fluidized bed portion, which is there at the bottom section of the bed, will carry the main load of the digestion, with the packed bed portion acting as the polishing section, because in the top packed bed the biomass concentration is very high. So whatever the pollutants that is left untreated in the bottom fluidized bed portion, that is removed in the top packed bed. So that acts as a polishing section. The specific features of a semi-fluidized bed bioreactor: a fluid reaching the packed section will lean in nutrients and will have less contribution to increase the cell mass, so as to clog the top portion of the bed and hinder the flow. That is one disadvantage. It may clog the flow of the fluid. Then microbial population can be controlled by periodically fluidizing the entire bed. That means if we remove the top restraint, that means the level of the top restraint if we increase, because it is a freely movable top restraint, by varying its position we can make the the particles present, microbial population present in the top packed bed, that can expand further if we move the top restraint in the upward direction, again replace it at its original position. A saving of 95% space can be achieved by using semi-fluidized bed bioreactor in place the conventional suspended growth wastewater treatment unit. Almost a complete removal of organic toxicants, nitrogen and BOD can be achieved with a residence time of a few minutes as compared to 1 to 3 hours in conventional processes. A comparison of the fluidized bed bioreactor with competing bioreactor in municipal applications are shown here. As you see, that specific surface area for bioreactor volume, specific surface area is for the mass transfer and for the reaction. So more is the specific surface area, more mass transfer and faster reaction is there. And another thing is the biomass concentration. That means more population is available to consume the pollutants. So one is the trickling filter, which is a packed bed reactor. The specific surface area is 12 to 30 and your biomass is up to 170. Rotating biological contactor, surface area 40 to 50 and biomass concentration is very low, up to 6. Hollow fiber membrane bioreactor, the specific surface area is 8 to 10, biomass concentration up to 22, whereas in a fluidized bed bioreactor the specific surface area is very high, 800 to 1200 and biomass concentration is less than the packed bed, but it is moderate, 30 to 40. So because of intimate mixing of the gas, liquid and solid phase, so all the surface of the particles are exposed for the transport and reaction in case of a fluidized bed. Then another table that is at the bottom, comparison of performance of bioreactors with respect to phenol degradation of wastewater. So condition is 500 gram per liter of phenol and the treated effluent it is CSTR bioreactor, packed bed bioreactor, fluidized bed bioreactor and semi-fluidized bed bioreactor. You see for the same, the semi-fluidized bed bioreactor gives a degradation of 9.1 kg of phenol per day per cubic meter volume of the bioreactor, and the treated effluent the concentration of that phenol is 0.008 to 0.45 milligram per liter, so very less, and your treatment efficiency is the highest among all these reactors. So for the design of the such semi-fluidized bed bioreactor, certain parameters that govern the performance are the properties of the particle, that is size, shape and density of the particle, properties of the fluid, density, viscosity and velocity, dimensions of the column and its configuration, initial static bed height, height of top restraint and ratio of top packed bed to the fluidized bed section. Semi-fluidization, some of the semi-fluidization phenomena that is based on the stages of semi-fluidization. Initially you have a fixed bed of particles. As you allow the fluid to flow in the upward direction through the bed, so the particles beyond the minimum fluidization conditions come to a state of suspension, and if a top restraint is not there, you see here top restraint is not there, then it is a fluidized bed simply, and if a top restraint is there and the particles just touching a particle, it may be a single particle also, it is touching the top restraint, then that is called the onset of a semi-fluidization. That particle will touch and held at the top restraint. Further increase in the fluid velocity, the layers of the solids attached to the top restraint will be seen. So the packed bed height at the top will gradually increase, and particles in the particle concentration in the bottom fluidized bed portion will gradually less. And if we further go on increasing the fluid velocity, a state will come where all the particles will be lifted to the top restraint and it will attach to the top restraint, and the bottom there will be no particles. So no fluidization, only packed bed at the top will be there. So these two things
can be varied. So one situation you say that height of semi-fluidized bed, which is now the top restraint position is changed. For the same fluid velocity, this was the height of the top packed bed and this was the fluidized bed, and the combination of these two was the semi-fluidized bed. So height of semi-fluidized bed, that is as it is written, 1 is nothing but height of the top packed bed 1 and height of the fluidized bed 1. But at the same condition, if we move down the top restraint, now the new position of the top restraint is this, earlier position was this. So with this you can see that the height of the top packed bed increased and the bottom fluidized bed decreased. So this combination of the top packed bed height and the bottom fluidized bed height is nothing but the height of the semi-fluidized bed. So but it is different from this semi-fluidization height because of the variation in the position of the top restraint. Again, there are different modes of fluid solid contact in a semi-fluidized bed. The mode 1A is the co-current 3-phase operation with liquid as the continuous phase. So liquid is moving upward in the continuous phase, gas is also moving upward, that is co-current flow, but the gas phase moves in the form of bubbles. These are the bubbles, and liquid is continuous. Whereas if the gas velocity is too large and the liquid velocity is less, the liquid will just in the form of film, it will move or trickle down like this, and the entirely the space will be occupied by the gas. Gas is continuous and liquid is discontinuous. Another thing, the counter flow operation, liquid is spread at the top, low density particles are used in this case. So mode 2A, that is counter current 3-phase operation with liquid as the continuous phase, inverse 3-phase semi-fluidization we get, where a top packed bed is formed at the bottom. And another mode is that counter current 3-phase operation with gas as the continuous phase, semi-fluidization represented by turbulent contact observer, where gas is the continuous phase and liquid trickles down here. The parameters for the design of semi-fluidized bed system, the values of minimum and maximum semi-fluidization velocity, the top packed bed height, total pressure drop in a semi-fluidized bed, gas hold up in a gas liquid solid semi-fluidized bed, heat and mass transfer characteristics. These are the parameters of importance in designing a semi-fluidized bed system. Experimental determination of the hydrodynamic parameters. So one schematic of one experimental setup is shown here. The one you see, this gas liquid disengagement section, this is. Second is the test section, this to this, and third is the gas liquid distributor section, this is. Then there are rotameters to measure the flow rate of the liquid and that of the gas. In this case, water is used, and water from a tank by means of a pump, it is allowed to flow in the upward direction through the bed, and by rotameters the flow rate is measured. So this system is connected to manometer to measure the pressure drop across the bed, and the top screen is this one is the top screen. So black dots are the solid particles, and there are hollow things, these are nothing but the gas bubbles, and rest of the things are the liquids. So liquid is by this it is mentioned. So as we have discussed the important parameters of the semi-fluidization, one is the minimum semi-fluidization velocity. So minimum semi-fluidization velocity is determined by varying the liquid velocity, as you see in the liquid velocity in the x-axis, and height of the top, height of the fluidized bed to height of the top restraint. St is the height of the top restraint. So that ratio, when it is plotted and you extrapolate the plot where it will equal to 1, that corresponding velocity will be nothing but the minimum liquid semi-fluidization velocity. So here the system of the experimentation is the liquid as the continuous phase and gas as the discontinuous phase, and liquid is the primary phase for the fluidization and semi-fluidization. That's why I talk about the liquid minimum fluidization velocity. Visually it can be observed when the particles will just touch the top restraint, that corresponding velocity is the minimum semi-fluidization velocity. Otherwise, from the plot of the ratio of height of the fluidized bed to the height of the top restraint, the extrapolation of that we will get the exact value of the liquid minimum fluidization, liquid minimum semi-fluidization velocity. So for different particle sizes, as you see, higher size particle, the liquid minimum semi-fluidization velocity is more, whereas for smaller size particle, the liquid minimum semi-fluidization velocity is less. And the top restraint is fixed. From the fixed bed, as we are increasing the fluid velocity, the height of the fluidized bed increases. As the height of the fluidized bed increases, the ratio of height of the fluidized bed to the top restraint again increases. So from a value of value between 0.4 to 0.5, it is increasing and extrapolated to a value of 1. That means the fluidized bed height, the fluidized bed just reaches the top restraint. So the variation of the bed pressure drop is shown in the right side figure. As you see, as we are starting with the zero liquid velocity, so no fluidization is there, that fixed bed is there, and as we increase the liquid velocity, the pressure drop increases, which obeys that of the Argon's equation. As per Argon's equation, just linearly it increases, the bed start to fluidize, then the pressure drop almost remains constant. A little rise in the pressure drop is because of the resistance that is offered by the top restraining plate to the flow of the fluid. Then there is a sharp increase in the pressure drop, that is at the minimum semi-fluidization condition, which is also called as the onset of semi-fluidization. A sharp increase in the pressure drop is there because the top packed bed, the pressure drop is much more than that of a bottom fixed bed. So from the different slope of the lines, we can get at the intersection, we can get the minimum fluidization condition and the onset of semi-fluidization. Then another is the maximum semi-fluidization velocity. The maximum semi-fluidization velocity is the fluid velocity at which the entire bed of solid particles is transferred to the top packed bed. Theoretically, this velocity corresponds to the terminal velocity of the particles, that is the free fall velocity. So the terminal velocity relations we know. If the operation is two types of regimes here is under consideration, because semi-fluidization need a high fluid velocity. So your Stokes law regime is not possible at all in case of semi-fluidization. Either it is intermediate flow regime or it is turbulent flow regime. Intermediate flow regime, the terminal Reynolds number is given by 0.1527, Archimedes number to the power 0.7143, whereas in turbulent flow regime, the terminal Reynolds number is 1.74 times of Archimedes number to the power 0.5. From this we can determine the terminal velocity, because the Reynolds number, as you know, it is the density times of the diameter of the particles times of the velocity upon the viscosity of the fluid. So as you see that this Hs is nothing but the initial static bed height of the bed, that top packed bed height is HPA. So the expanded bed edge is plotted, with that of the fluid mass velocity or the fluid velocity. Fluid mass velocity is mentioned. It may, the fluid may be liquid or gas, because it is a pressurized system. If gas is there, then your density of the fluid will be different. Simply volumetric flow rate has no meaning, or volumetric velocity has no meaning. That's why mass velocity is used in general. So the bed voidage, as you see, expanded bed voidage reaches here for the maximum semi-fluidization condition. The expanded bed voidage reaches 1, and your HPA upon HS. Otherwise, there are two ways. Either the expanded bed voidage can be plotted with the fluid mass velocity, or HPA by HS can be plotted with the fluid mass velocity. When the HPA upon HS becomes 1, okay, that is nothing but the maximum semi-fluidization velocity. So maximum semi-fluidization velocity theoretically can be determined from the particle terminal velocity relationship, and experimentally can be determined by these plots. There are summary of correlations and models for minimum and maximum semi-fluidization velocities. You can see these correlations. Many people, they have carried experimentation and their research on different particle systems, different types of beds, different types of fluids. So depending upon the number of operating variables they have, different types of correlations have been obtained, and some of the correlations are in the dimensional form, and some of the correlations are in the dimensionless form. These relations can be used for the calculation of the onset of semi-fluidization velocity or the minimum semi-fluidization velocity. Then there are systems. This is for liquid solid system, these correlations, and for gas liquid solid system more parameters are there. So correlations are also available for gas liquid solid system. Then similarly for maximum semi-fluidization velocity, we have the correlations like this, both dimensional form and dimensionless form for the liquid solid system, and for gas liquid solid system the correlations are like this. So using this correlation we can determine the minimum semi-fluidization velocity and the maximum semi-fluidization velocity. Then height of the top packed bed. A peculiar characteristic is observed for the formation of the packed bed and the breakage of the packed bed when we increase the fluid velocity and decrease the fluid velocity. As you see here, the plot to the left, the superficial velocity is varied, and ordinate, that is HP upon HS is there. As already I have mentioned that the extrapolation of HP upon HS will give us the maximum semi-fluidization velocity, and so the HP upon HS is 0 for the fixed bed. So this is the 0 for the fixed bed up to this, and this is the minimum HP upon HS is 0 up to the initial fixed bed and the fluidized bed condition, when no particle is touching to the top restraint, and as the particle will touch the top restraint, that time, okay, change of slope will be there. That means it will not be 0, its value will increase because it is HP upon HS. So that is increasing like this, and if we extrapolate that to the value of 1, then the corresponding velocity is the maximum semi-fluidization velocity that is determined. Here it is the onset of semi-fluidization velocity or the minimum semi-fluidization velocity, it is the maximum semi-fluidization velocity. But when you decrease the fluid velocity from this, so the path will be like this. Path will be like this here. Path will be like this. This is for the increase in the fluid velocity, this is for the decrease. So the top packed bed remain intact even if you have decreased the fluid velocity near to the minimum fluidization velocity. This is the minimum fluidization velocity. Up to the near to the minimum fluidization velocity, the top packed bed remain intact. That is the inertia of motion, inertia of rest, those things are there. So because of that inertia of rest, it remains there. Suddenly within a very narrow range of the fluid velocity. Only this, all the particles they fall down to the bottom, and the expanded bed height. The expanded bed height is not that much. Expanded bed height is not that much. So that means it is suddenly falling and becoming equal to the initial static bed, like that. Then there is a clear zone is there. So the clear zone, I can show here another that video to convey you. कौन पावर पॉइंट क्लोज क्यों नहीं हो रहा है? सिस्टम में कुछ प्रॉब्लम हुआ? ओके So here you can see in this video, this is a fluidized bed, and the bottom at the bottom there is a fluidized bed, and with increase in the fluid velocity gradually, the fluid velocity is increased gradually. Now you see that top of the packed bed is formed. So bottom the particle concentration is more, and just below the top packed bed the particle concentration is quite low. So that and sometimes we get a clear zone here, that between the bottom fluidized bed and the top packed bed a clear zone is there, and during defluidization the clear zone is more and more. Okay, the variation of bed volume fraction without solids, which is called as the clear zone with the liquid velocity, as you see. So the clear zone height for this increase is like this, then it is this, then gradually it becomes like this, then a sudden valley is here in the clear zone. Okay, the particles fall in this a narrow range of velocity, it falls to the bottom fixed bed, becomes the bottom fixed bed. Because of that the clear zone variation is there. So you can see a clear hysteresis loop for the formation and breakage of the top packed bed is there, and also the volume fraction of the entire bed without solids, that is the clear zone. So the operation is very complicated, because we have to take care of all these things, otherwise the appropriate semi-fluidization and the performance of the bed cannot be there. Certain correlations are also developed for the prediction of the top packed bed height and the bed pressure drop. These correlations are listed here, as you see, and for the liquid solid and gas liquid solid systems, the correlations are in the dimensionless form. These are the correlations are there. This is the packed bed height to the height of the static bed is correlated with the this is the velocity and onset of the semi-fluidization, then the superficial velocity. US is the superficial velocity of the fluid and a superficial velocity at the onset of semi-fluidization. So two different correlations are there for the same thing, because one is for HP upon HS, the value less than 0.42, another is for greater than 0.42. The dependency of the HP upon HS upon the ratio of the model for the prediction of the pressure drop across the bed. It is based on the fundamental force balance and semi-empirical correlations. Empirical correlations are combined together. So the pressure drop across the semi-fluidized bed is the combination of pressure drop across the fluidized section at the bottom plus the packed bed section plus the pressure drop due to the position of the top restraint. So that the semi-fluidized bed pressure drop is written as a fluidized bed pressure drop plus the top packed bed pressure drop plus the pressure drop at the top retaining plate. The pressure equivalent to the buoyant weight of the whole of the solids can be taken as the fluidized bed pressure drop, because at that ideally that is the fluidized bed pressure drop. So which is written by this fluidized bed pressure drop, which is nothing but 1 minus epsilon f. Epsilon f is the voidage in the fluidized bed, then density of the solids minus density of the liquid multiplied by height of the fluidized bed, and this is ideally equal to that of the mass of the particles in the bed multiplied by gravity, that becomes the weight of the bed upon the cross sectional area of the bed. For the prediction of the packed bed pressure drop, Organised equation can be used. This is the Organised equation, you know it very well. Then the semi-fluidized bed pressure drop can be calculated from the following equation. That means combining this, that is the weight of the particles in the bed to the ratio of weight of the particles to the bed to the column cross section plus the Organised equation. So this is the fluidized bed pressure drop and this is the packed bed pressure drop. Packed bed pressure drop. Prediction of packed bed height, pressure drop and gas hold up in gas liquid solid semi-fluidization. The semi-fluidization would occur when the bed expands to such an extent that the hold up of the solid in the fluidized bed. Hold up means the fraction of the solids in the fluidized bed equals to the solid hold up at the onset of semi-fluidization. So which is nothing but the fraction of the solids in the semi-fluidized bed can be mentioned. So it is the mass of the solids upon the density of the solids, that is the volume of the solids upon the cross sectional area multiplied by the height of the semi-fluidized bed, which is nothing but the volume of the semi-fluidized bed. So volume of the solid particles divided by the volume of the semi-fluidized bed is nothing but the solid fraction at the onset of semi-fluidization, and the void fraction, which is nothing but the sum of the phase fraction of the gas and that of the liquid. So which is given by the equation, that is the equation of kx model. One kx model is there, which is in the gas solid fluidization that might have been discussed. K is nothing but the ratio of the wake region to that of the ratio of the bubble region, and x is nothing but the fraction of the solid present in the wake. So when a bubble is moving in the upward direction, the bubble actually, the bubble lower portion of the bubble is like this. There is chance that this is the wake region here, and a chance that the particles may present here also in the wake region. And if the particles are of size more than 1 millimeter, okay, the x becomes 0. X is 0. So for that, the equation can be written in terms of k, and that equation is nothing but superficial liquid velocity minus superficial gas velocity times of this k. K is nothing but the ratio of the wake region to that of the bubble region. This is the bubble and this is the wake. So that ratio is k upon the particle terminal velocity times of 1 minus epsilon g is nothing but the gas hold up, then k times minus k times of the gas hold up, which is, that means volume fraction of the gas in the bed. So all other things are like this, the notations as you see, and this is the expression, and this k, that how much the volume is the wake and the bubble is there. So that ratio, that k is given by empirical relation, and the empirical relation is 0.398 UL to the power 0.246 times of Ug to the power minus 0.646. That means the dependency, as you see, with increase in liquid velocity k will increase, whereas with increase in gas velocity k will decrease, because the exponent you see it is positive, here it is negative. And from the material balance model, for the height of the packed bed section in a semi-fluidized bed can be expressed, that is height of the packed bed is nothing but the mass of solids by the density of the solid, volume of the solids upon the cross sectional area of the vessel minus height of the semi-fluidized bed times of the fraction of the solid upon the fraction of the solids in the packed bed minus the fraction of the solids in the entire thing. So for the prediction of a pressure drop in the semi-fluidized bed, the following model equations are used, which is a combination of the fluidized bed pressure drop and the packed bed pressure drop, as you see here. And the fluidized bed pressure drop is already we have discussed, is this, and your solid fraction is calculated by this equation, already we have discussed. And in a three-phase system, gas, liquid, solid, your sum of the gas fraction, liquid fraction and the solid fraction is equal to 1. So that the pressure drop in the packed bed can be your theta L times of delta P F, that is the pressure drop in the fluidized bed. LS superscript means it is for the liquid solid system, and theta L is nothing but your this phase fraction when you consider the gas and the liquid only, without that of the, based on the gas and the liquid without solids, that is the phase fraction of the liquid, another notation, another quantity. Similarly, theta g is nothing but the phase fraction of the gas based on the gas and the liquid only, no solids. So then here in this equation, plus theta L times of density of the liquid plus theta g, that is phase fraction of gas based on gas liquid times of the density of the gas times of the height of the packed bed multiplied by g. This is the top packed bed pressure drop. And your theta L plus theta g without solids, this constitute to 1 actually. The frictional pressure drop between the liquid and the solid and can be expressed by finding equation. So in the liquid solid system, the fluidized bed pressure drop is nothing but 4F. This is the F is the friction factor, 1 upon DE. It is the equivalent diameter of the vessel. D is the equivalent diameter of the vessel times of 1 upon 2 density of the liquid times of this is the liquid superficial velocity upon the liquid hold up of the liquid in the packed bed. P means packed bed, square of that okay, times of the height of the packed bed. So and the equivalent diameter is calculated from this relation, where the notations are have their own meaning, that is epsilon sp is nothing but the solid fraction in the packed bed, and theta g is nothing but the volume fraction of gas based on the gas and the liquid only. Phi s is the sphericity, dp is the equivalent diameter of the particles. So the modified friction factor relates the liquid Reynolds number and empirically correlated by Chern and co-workers, that they have given the expression that the friction factor is the 0.1075 plus 6.359 Reynolds number to the power 0.368, and the Reynolds number here is defined like this. This is the DE, that is the equivalent diameter of the channel, density of the liquid, superficial velocity of the liquid upon viscosity of the liquid times of the phase fraction of the liquid in the packed bed. And the gas hold up in the packed bed based on gas and the liquid phases, that theta g, the expression is the empirical relation. The expression is this 0.0296 liquid velocity to the power minus 0.35 and gas velocity to the power 0.977, which means that with the increase in gas velocity theta g increases, and with the increase in liquid velocity theta g decreases. For the prediction of average gas hold up in the semi-fluidized bed, the following model has been proposed by Chern and co-workers. So epsilon g SF, that is the volume fraction of gas in the semi-fluidized bed, is nothing but HPA upon HSF times of epsilon g P, that is for the packed bed, plus 1 minus HPA upon HSF times of epsilon g. Epsilon g is the phase fraction of the gas in the fluidized bed. For the gas hold up calculation in the fluidized bed section in the dispersed bubble flow regime, here you see that epsilon g, so ug, that is the gas velocity upon the phase fraction of the gas, is nothing but superficial gas velocity upon 1 minus the solid fraction epsilon s plus superficial liquid velocity upon 1 minus epsilon s plus uo, where this uo is nothing but the buoyancy velocity, and that buoyancy velocity is given by this relation. uo is nothing but 10.16 plus 14.88 square root of the superficial gas velocity upon 1 minus the phase fraction of the solid. So these are the model equation. These model using these model equation, height of the top packed bed, phase hold up, pressure drop, all these things can be calculated, and experimentally also the values have been calculated, and for the gas hold up correlation is available. The experimental values of a semi-fluidized bed gas hold up has been compared with the semi-fluidized bed gas hold up calculated from these model equations, and the experimentally one correlation is this, where this is the volume fraction of the gas in the semi-fluidized bed is correlated with these parameters. The first one MO is the Mohan number, EO is the Eötvös number. These two numbers are the combinations of Weber number, Reynolds number, and the Froude number. Then liquid phase Froude number is there, gas phase Froude number, and this is the density of the liquid to the gas. This is the ratio of the diameter of the particle to the diameter of the bed, and this is the aspect ratio, means diameter of the particle to the height of the bed, that aspect ratio. Sorry, the last one is the diameter of the vessel to the height of the vessel, that is the aspect ratio. So a comparison, as I have told earlier, so this is from the model equation, these values have been predicted, but experiment gives this type of things. So when the at the onset of semi-fluidization, you see because of the presence of the top packed bed is forming, suddenly the gas hold up increases, and tremendously it increases. very significantly it becomes high, because in a pressurized system the residence time of the gas bubbles will be more and the phase hold up of the gas will be more, so gas hold up increased significantly. And for the systems where the mass transfer from the gas phase to the liquid phase and subsequently to the solid phase is there, such type of systems high gas hold up is required. And you see that with little bit semi-fluidization, to a lesser extent also, we are getting very significantly very high gas hold up we are getting, that is the advantage. So for systems like the biological wastewater treatment, where a first order type of this reaction is there, so a semi-fluidized bed, which is the combination of the fluidized bed at the top, that is a kind of CSTR, and a packed bed at the top, which is a plug flow reactor. So that combination is the most suitable one, and the gas hold up is also significantly high. So for aerobic biodegradation of organic pollutants, the semi-fluidized bed bioreactors are the suitable one. And a new correlation have been proposed for the prediction of gas hold up in the semi-fluidized bed, that is in terms of liquid velocity and gas velocity. You see this gas hold up is a strong function of gas velocity, but it is a weak function of the liquid velocity. From the exponent it is clear. So this is all about the design aspect of the semi-fluidized bed based on the hydrodynamic perspective, and which is required for the application of semi-fluidized bed system in the waste management and sustainability. Thank you. Questions please.
Hello, I have one question. What type of packing material can be used in this semi-fluidized bed?
It is not a packed bed alone, so the packing material is not a subject matter actually, because it is a fluidized bed. Subsequently the fluidizing particles are forming a packed bed at the top, and it is not normal the packed bed what we get for the dumping of the particles. The void fraction of the top packed bed is always less than that of a normal packed bed where the particles are dumped. Because of that, significant high pressure drop also we are getting. But in semi-fluidization, as per your question, the semi-fluidization, that the packing is not a matter, rather it is a fluidized bed. But the fluidized bed, the free expansion of the bed or the height of the fluidized bed, we are restricting by a top restraint, so that at the top we are getting a packed bed. And to a little extent, if the packed bed is there, I have already mentioned that for certain applications it is good, because bottom we are getting a continuous tied system, and at the top it is a plug flow type of system. Bottom there is fluidized bed and top there is packed bed. So here this whatever that reaction is there, which is not done in the bottom fluidized bed for the wastewater treatment, as the biomass concentration at the top packed bed is quite high, that will act as a polishing section. That means the pollutants will be removed, whatever the pollutants left, so that the effluent that we will get will have pollutants of very low concentration. That is the advantage. It is not the packed bed like racing ring, ball saddles, etc. we consider. Okay, those are the things rarely we use in the fluidization. Rather, the fluidizing material for like gas system we use smaller particles we use. Liquid system little larger particles are used for the fluidization. In gas liquid solid system, if liquid is the primary phase, then also larger particles, moderate size particles more than 1 millimeter to 10 millimeter can be used. Such particles of different material, maybe of polystyrene for application as a biological reactor, where the density is little more than that of water, or it may be heavier particles for other applications like might be having the specific gravity 2, 3, 4 like that. It is possible.
If it is little more than the water means it will remain at the towards the bottom of the reactor, the fluidized.
No, a little more means it is like say suppose coal is 1.5. Then your suppose a little more means it is not exactly close to water, because in a three-phase system simply liquid with you are fluidizing, then only liquid is there without absence of gas. The particles will be at the bottom, okay, bottom fixed bed. But if gas phase is there, gas what it does actually, hydrostatic pressure decreases because of the gas fraction in the bed, so that the particles will move in the downward direction in that case. Otherwise, with increase in the liquid velocity, the particles will move in the upward direction. But here the particles may be starting from coal. Coal is of specific gravity 1.59 like that. So to any higher density things, that type of particles can be used here. Any more questions? If no more questions, I stop here. Thank you all.
to moist it. पूरा पकड़ो. Now we will weight the sample. To moist it. पूरा पकड़ो. Now we will weight the sample. पानी ना. अच्छी सर्कल खोजता हूँ. Total 380 grams of weight sample we have taken. 380, 200, 150 and 10. Now we will put the weight moist sample into the drying column. Now the air is coming out to dry this moist sample, and that is how the dry fluidization braid act. Hot air will pass through it, will flow from downward to upward, drying the materials kept in this. Air is flowing upward direction in upward direction and the grains are drying down. Now fluidization, dry fluidization is taking place by the hot air. Drying is happening rapidly in the fluidized bed. This is the dry fluidized bed. From this we can check it that dried, the sample is dried. To moist it. पूरा पकड़ अच्छा dry fluidization is taking place by the hot air. Drying is happening rapidly in the fluidized bed. This is the dry fluidized bed. From this we can check it that dried, the sample is dried. calculating the weights, we can see that 200 grams, 100 gram, 20 gram, 10 gram, 5 gram and 1 gram weight is used. Total weight is 336 gram, which is less than 380. That means our sample is dried properly. Thank you so much.
Is it something? Okay. Initially, the difference between spouted and fluidized bed makes between the spouted and fluidized bed makes the difference at the distributor itself. If you can see it, the distributor will have number of holes passing to pass the air to the bed, but this is the fluidized bed. When a certain point of diameter is kept at the center, which air could pass through the bed, then it makes the difference of the spout and this is the difference between spouted and the fluidized bed. This is the basic first. Initially air has to be passed through the bottom of the conal section here, because when the air has passed from narrow end to the wider range, this is what it has designed. From here a material is fixed here, it is called a fixed bed. Initially what will happen, in spouted bed has gained tremendous attention in 1950s. In Canada, initially they have used for drying of wheat, drying purpose initially they have started. Now it has many applications in not only in drying, coating applications, especially in pharmaceutical they are applying a lot. Based on this, I have taken a material called cellets. Initially these cellets are used as these are made up of API. Upon this, there are many types of coating purpose. Depending upon that, initially the cellet particles which are made up of microcrystalline cellulose, beads have been taken which are of 100 micron. These are the bed material size we are using today at different bed height. Initially it is in conical section. So when the spout is given here, a fixed amount of bed has been used. This is called fixed bed, spouted fixed bed. When the required amount of velocity has been applied through the bed, then here two types will be classified. One is internal spouting and external spouting. Internal spouting makes the fixed bed, internally the spouting will appear here only. This resembles that the bed expansion will take place from here to here. For example, bed expansion will happen. This everything can be happened inside only. The variation what we can observe is bed expansion only. Once the internal spouting has developed, if we go on increasing the velocity, then we can find out the external velocity, external spouting. So external spouting will be like, this is the packed bed, expansion will be there and spouting will appear here, like has we seen many places like spouting, spout like fountain, how it looks. These are three types. One, this spouting is symmetric spouting, asymmetric spouting and dilute spouting. Symmetric, asymmetric and dilute. As everyone knows that from axial radiation, this is the symmetric. Asymmetric, from one direction it moves the particle and fall through the other direction. This is called asymmetric. And dilute, the spouting will appear but all the particles will be distributed whole around the column. That's why this extension part of the cylindrical column we have fixed. Then we can observe the dilute spouting. In dilute also we can see the particles which are clusters, bubbles can be appeared at the bottom of the bed, and it in air pockets will appear, and the particles clusters has been appeared also in this. Everything we can see here clearly. First initially we will pour the bed sample here. Anyone is having any doubt? Shashi, go now. Pose it. Okay. Now this is the fixed bed height. It is 12.5 centimeter. Manometer is required, so that we can, rotameter is required to measure the velocity of the air. It is in RPM, LPM it is, that we have to convert it based on the velocity we have given. And this is the manometer. From with this manometer we can identify initially the internal spouting will happen. So when the internal spouting will happen, velocity versus pressure drop, if we draw a graph between these two, in internal spouting, linear graph can be observed. Means if we increase the velocity, pressure will also increase simultaneously. Once external spouting will happen, then the pressure drop will fall and maintain constant pressure. For this purpose, we have all this rotameter and manometer we have been fixed, and the bed material we have used are cellets, which is 1000 microns. So that can we start the experiment. And we have given 120 LPM. Then we can see that bed expansion has not been there, and the pressure drop. Here the bed expansion has happened, then the spouting is appearing. This is called the external spouting. Spouting will appear. Why? Because the velocity is not in the one direction. Velocity of the air is not in the one direction. When we increase the velocity, spouting has been increasing. Spout has been increasing. And it is like the particles which are spouting, which have gone through the space, then it is like counter current flow has been, the particles are moving down. This can be observed here. Shall I? Been appearing, only the particle movement have been there. When the velocity has been increased, this is the C 100 LPM. Then the external velocity has और ज़्यादा air. See this spouting. Velocity और ज़्यादा sir. Explain this. I will explain this point. Sir, close. Drop we'll get is high. Delta P is high based on differences between the manometer we have connected. One is H1 and H2. The difference between this is H, and pressure drop delta P equals to rho CH. Using this formula, we will calculate the pressure drop. Initially, when the particles are packed like this, the required amount is, if not sufficient, the air will flow, the velocity of the air will percolate through this, and it passes through the packed bed. Then there is no movement of the particles takes place. That is at static condition only, but pressure will be measured here is pressure drop will be high. When internal spouting will happen, the pressure drop decreases. Why? Because the particles, it lifts the particles up. Here the drag acts high because the velocity is as compared to the velocity lifts, the particles will suspend or the particles will move. This will appear because we are adding the spout at the center point. The spout will appear, then the velocity will reduces. Here when we go on increasing the velocity, what is happening means the particles which are getting agglomerated. This is because the clusters have, sir and ma'am have discussed earlier that all these particles, air will flow like pockets, and the particles will get aggregated here. Once it reaches its means gravity when it is low, when it is high, the particles will fall down. Because of agglomeration, the density will increases. When agglomeration happens, the density of the particles all together will be high and the particles will fall down. Any questions? Like you can see this preservation. Okay. Can be takes place here. Here, when increasing, particles are increasing high. Spout has appeared, and that difference has been very less. We can see this, all the particles, this is the air pockets, and this is the clusters we can appeared here. And this asymmetric spouting, because spouting is happening from one end and the particles are falling from the other end. You can observe this direction. Almost the particles all are in suspended stage. This stage is called the diluted spouting. Getting the maximum height it has reached. The height direction of the particles. When spouting is happening, the velocity particles are forming like this, and this is the velocity of A with respect to spouting. This is the particles are traveling along with the wave in upward direction. That it means like co-current spouting. When it reaches the maximum, when ut is high, then velocity particles are falling back, and particles are moving in counter current. It is opposite to the velocity of the air. As I already told, asymmetric spouting. Asymmetric spouting means the velocity of the particles, these are moving like this and falling in opposite direction. It is not appearing at the center of the axis. If the spouting is appearing here, means particles are moving in this direction and falling in this direction. It is called symmetric. This is asymmetry. Are coming in this entrainment. These particles are coming down, which is called counter current particles. Counter current flow is happening here. They can ask me. No doubts?
Solid and gas solid. Hydrodynamics of the gas solid system and liquid solid systems. Here hydrodynamics means how the bed behaves, that includes the determination of the minimum fluidization velocity, pressure drop, and bed expansion, how much it is expanding during the fluidization process. So first I will show the hydrodynamics of the gas solid system, then we will show the hydrodynamics of the liquid solid systems. And here you can see this is the rotameter. From this side you can show this. We will see that how the bed height is changing, that is bed materials getting expanded and bed height, total expanded bed height, then from the expanded bed height we can calculate bed expansion ratio and the bed fluctuation ratio. And similar, here the bed expansion ratio is the expanded height divided by the static bed height. Now bed fluctuation will be the expanded height, it fluctuates within some minimum and maximum value, that is minimum expanded height, maximum expanded height. We can take average of that, which will be the average expanded height to static bed height is the bed fluctuation ratio. So and from the pressure drop versus velocity plot, we can get the minimum fluidization velocity. Now here just I will show that how the bed is getting expanded. Then with the repetition of that experiment, that is by varying the flow rate, we can get various pressure drop, and manometer is here in between. Here it is manometer is shown, and from here we can get the differential height. So multiplying with the density of the liquid, that is fluid, which is taken in the manometer, we can calculate the pressure drop. Now after getting number of readings of the pressure drop against the velocity, we can plot that delta P versus velocity. From that we can get the minimum fluidization velocity. And fluidization occurs just after the minimum fluidization, that is in the minimum fluidization, all the materials are ready to move up and down. Because in the static condition, when there is no supply of the air, the bed behaves like a packed bed, and with increase in the velocity of the superficial velocity of the fluid, the void among the particles get expanded, and gradually with further increase of the velocity of the air, the bed materials are free to move. And this we can see now here the rotameter, just from this side you can show. First we can see here the rotameter reading is 0. You can see that now the bed is static, it is not getting expanded, and pressure drop also, it is almost same. There is no slight because completely 0 is not maintained, so that it is almost same, no pressure drop. You can see here by increasing the flow rate, now we increase to 5 liter per minute. Still it is not expanded because initially the air fills the voids among the solid particles. Now with further increase in the flow rate, we can see some particles here in the bed. You can see some particles are getting movable or getting expanded from its original position. It is the entire bed is not expanded, and with further increase in the flow rate, now you can see I made it 10 liter per minute flow rate. Now with this you can see the entire bed material are getting expanded or movable. So here we can see that this is the height up to which the bed is getting expanded, that is roughly it is 18 centimeter, and that means expanded bed height is the 18 centimeter. It is coming up to 18 centimeter. And if you say that what is the minimum, this is coming maximum bed height up to 18 centimeter. The minimum expanded height you can see it is coming 16, whereas static was, just one second I can show you the static bed height. It is nearly 15, 14.5. So minimum with the 10 liter per minute you can see, and with this the maximum expanded height, you can show there. Here it is coming around, now it is more than 18 it is coming, so it is about 19, and minimum is coming about 16. So thus average of this, if you take 19 plus 16 divided by 2, that is the average expanded height. That divided by 14.5 will give you the fluctuation ratio, and 19 divided by your 14.5 will give you the expansion ratio. So then with this 10 liter per minute flow rate, we can see that here the manometer, it is on this side, it is, you can see here, and on this side up to here. That means delta H is coming around you can see 4, around 4 it is coming. So delta H multiplied, here it is potassium permanganate is taken as the manometric fluid, and any fluid whose density is more than the density of the fluidizing medium can be taken in the manometer for measuring the pressure drop. Here we will get the delta H, differential height in the two limbs, multiplied with the density of the manometric fluid will give you the pressure drop. So this is about the hydrodynamics of the gas solid fluidized bed. Now we will move to the liquid solid fluidized bed.
Now the participants, I am going to demonstrate the characterization of a liquid solid fluidized bed. A very simple setup available in the laboratory that I am going to show you. Liquid solid fluidized bed, liquid is stored in a tank. As you see, that liquid is there in this tank, and this liquid is pumped by means of a pump here at the bottom, and this liquid flows in the upward direction, and this is the fluidized bed. This portion is the fluidized bed. In the fluidized bed, particles are there, and this is a batch liquid solid fluidized bed, where solid particles are already dumped in this bed, and the height without the flow of the liquid, it is the static bed height here. So when I will allow the flow of the liquid through this bed, and liquid will flow through one distributor plate, it will enter to the vessel, and the liquid will rise, and finally liquid will come out, and recirculation of the liquid is there in this system. The pressure drop for this can be measured using manometer. Already other experiments you have learnt how to measure the pressure drop using the manometer. So only I want to show you that earlier you have seen that gas solid fluidized bed, which is called as the heterogeneous fluidization. Gas solid fluidization is heterogeneous fluidization, where gas bubbles are formed, and depending upon the velocity of the gas, smaller bubbles are there. As you increase the gas velocity, bigger bubbles are formed, and finally you reach at the slug flow regime. And in the form of a cloud, the solid particles move with the bubbles of the gas, which is not in the case of liquid solid fluidization. Liquid solid fluidization is called the particulate fluidization, smooth fluidization, or homogeneous fluidization, where uniform distribution of the particles are seen. In gas solid fluidization, heterogeneous, the bed is heterogeneous because large bubbles are there, smaller or larger bubbles are there. But in liquid solid, the liquid is well distributed, particles are well distributed, uniform fluidization we will get. And as we increase the liquid velocity through the bed, after the beyond the minimum fluidization, first there will be no change in the height of the bed up to the liquid velocity reach the minimum fluidization velocity, and beyond the minimum fluidization velocity, if we further increase the liquid velocity, then expansion in the bed will be there. That I am going to show you. So the liquid, which is water here, stored in a tank, and that is getting pumped by means of a pump, and there is a bypass line. Now the bypass line is fully open, so that there is no flow of the water through this bed. Now if I close this bypass line little, so then flow will be there through the bed. Now you see that liquid level is increasing, that means liquid is entering to this bed. But as the liquid is entering, moving in upward direction, but there is no motion of the particles. Particles are not moving. If I further increase the liquid flow rate by closing the bypass line, liquid velocity will increase gradually. Liquid velocity is increasing.
there, bed is not getting disturbed. Some dust particles are there, okay, those are just in the form of agitation over the bed is there, but the glassweed solid particles, they are not moving. So if I gradually increase this, the liquid velocity by closing the bypass line, by reducing the bypass flow, now the minimum fluidization has not reached, so gradually I am increasing the flow of the liquid through the bed. So as the flow of the liquidity through the bed is increasing, the liquid velocity is nothing but the flow rate divided by the cross-sectional area of the bed, that is the superficial liquid velocity. So the superficial liquid velocity is also increasing. And as the liquid velocity is increasing, you know whether the flow of the fluid is either in the Stokes law regime or it is in the Newton's law regime. Depending upon the flow regime, either it depends upon the first power of the velocity or the second power of the velocity. That means with increase in the fluid velocity, the drag force that the liquid exert on the solid particles will increase, whether linearly it will increase or it will increase with the square of the velocity, that depends upon the flow regime. But it is a low flow rate, so it is a laminar flow kind of thing, and in this laminar flow, low flow rate, it will depend upon the first power of the velocity. Still that liquid flow is there. Now you see the other line, liquid is coming, the water is coming, but this flow what is happening through the bed is not sufficient to make the bed fluidized. Now the bed is just getting fluidized. Now you see that bed started moving, little bit the height increase is there. So minimum fluidization is reached. If I further increase the liquid velocity here, then bed expansion will be there. And you see little more. If I further increase the liquid velocity, the bed height is increasing. With the increase in the liquid velocity, I am increasing the liquid velocity. You see the proper fluidization is there, and here you see that uniform distribution of the solids are there, no bubbles are there. It is the liquid solid fluidized bed. Okay. Smooth fluidization or particulate fluidization is there. If I further increase the liquid velocity, this is the way the bed height is increasing. Gradually the bed height is increasing. So you are getting a smooth fluidization here. So the difference between gas solid fluidization and liquid solid fluidization you can see. Now I will make this a three-phase fluidization by allowing the gas bubbles. As you see here, this water storage tank is a shallow water storage tank, and as per the capacity of the pump and because of the recirculation of the water here, you see that the bubbles are forming here, and those bubbles which are forming because of the vortex of the liquid here, that means the entrapment of the air to the water. So those bubbles are carried out by the pump, and those bubbles sometimes it is coming in the bed. Initially at a low flow rate it was not there. Now you can see some of the bubbles are moving. Okay, so this air bubbles are moving, but if I will decrease the if I will decrease the water, air bubbles will be withdrawn by the pump, and that will enter into the fluidized bed. Of air bubbles are flowing. It is a kind of three-phase fluidization you are reaching almost. But it is the air is not, we are not supplying any extra air
through any sparger to the bed, but this is because of the entrampment of the air to the liquid, and which is carried out by the pump to the bed, which is coming. So this is the liquid solid fluidization that has the difference over the gas solid fluidization. Thank you all. If you have any doubt, you can ask. Thank you.